Hi and welcome to the Appendix, the Python crash course. And it's actually more than just a crash course, so it's a very detailed and practical introduction to Python coding with real-world examples taken from the business and finance world. So in case you haven't worked with Python before, or if you need a refresher, then this is the right place here. So it prepares you for the main part of the course, no more and no less. And in total, there are 5 subsections. So we have Appendix 1, 2, 3, 4, and 5. And section 1 starts with the very basics of Python and also some finance basics. And for example, you can find there variables, data types, lists, dictionaries, operators, conditionals, and all that basic Python coding stuff that you will definitely need for the course here. Then second, we have user-defined functions. So creating your own functions, which is very important if you want to create more complex code and if you want to create classes. Then Appendix 3 continues with the data science stack, and it covers NumPy, Pandas, Matplotlib, and also Seaborn. And we will heavily use these packages and libraries in the main part of the course. Then in Appendix 4, you can find some advanced Pandas time series topics like time zone conversion. And finally, you can find an introduction to OOP and creating classes in Appendix 5. So in the main part of the course, we work with powerful backtesting and trading classes. And in case you haven't worked with or created classes before, then here is a very simple and intuitive introduction. So many students don't really like classes, but with the right tutorial, it's really simple and fun. So this is the appendix, and in the very next lecture, you can find all the materials, so the Jupyter notebooks and also the data sets for all 5 subparts. So you just have to click here on resources and to download here the zip file. Thanks for watching, and see you in the next lectures and sections. Bye.
Hi and welcome. This video is about the time value of money concept, which is probably the most important and most fundamental concept in finance. And actually the basic idea behind the time value of money concept is that $1 today is worth more than $1 tomorrow. And this is the case because you can invest or save your dollar today and earn a positive interest until tomorrow or until in 1 year, for example. So when somebody offers you the option to give you $1 either today or in 1 year, you should actually select today and invest or save the dollar to earn interest on it. So let's have a look at some examples here. And first of all, we have $100 today, and we can save the $100 at an interest rate of 3%. And second, again, we have $100. And we save our $100 for 3 years at an interest rate of 3% per year. And the question is now, what value do we have after 1 year or after 3 years? And this is also the so-called future value. So $100 is the present value today, and the value of the $100 in 1 year or in 3 years is the future value. And calculating the future value is actually pretty straightforward. So this is here the formula. So we have the present value times 1 plus r. So r is the interest rate, for example, 3%. And then to the power of n. So n is the number of periods. And actually the concept of compound interest or interest on interest is deeply embedded in the time value of money concept and in the formula here. So when an investment is subject to compound interest, the growth in the value of the investment from period to period reflects not only the interest earned on the original principal, so here $100, but also the interest earned on the previous period's interest earnings. So the interest on the interest. So let's go to the solutions of our examples here. And first of all, we have $100 today. and we can actually save or invest the $100 at an interest rate of 3%. So here we have 1 plus R is 1.03. And in 1 year, consequently, we have $103. So this is the future value of our present value, 100. And the calculation here is pretty straightforward. So here it is. And now let's go to the 3 years example. So we have $100 today, and then we save the $100 for 1 year. And after 1 year, our $100 worth $103. And then we again save or invest the $103. And we not only get interest on our original principal, 100, but also on the $3 interest that we earned in the first period. So this is compound interest or interest on interest. And then again, we invest our total value after 2 years for another year here, again at an interest rate of 3%. And finally, we end up at a value of 109.27. So that's the future value after 3 years. And this is here the calculation. All right, now let's go to present value and some examples here. So we want to have $110 in 1 year, and we can save at a rate of 4.5%. And the question is, how many US dollars do we have to save today to get $110 in 1 year? And the same example we also have here for an investment period of 3 years. So how many US dollars to save today at an interest rate of 4.5% to get $110 in 3 years? So in these examples here, we have the future value, 110. Then we have the interest rate, and we actually have to calculate the present value. And we can do this by discounting the future value. So the computation of the present value works actually in the opposite direction than calculating future values. And this is the formula here. So we have to discount the future value and divide the future value by 1 plus R to the power of n. And let's have a look how it works in practice here. So we have the future value of 110 in 1 year, and we discount it for 1 year at an interest rate of 4.5%. And we actually get here 105.26. So we could say that getting $110 in 1 year has the same value as getting $105.26 today. And of course, the calculation here is pretty straightforward. And let's go to the second example. So we have $110 after 3 years, and we discount the 110, so the future value. And we actually have 3 periods, and in each period we have an interest rate of 4.5%. And finally, we end up at a value today, so the present value of 96.39. So this is the time value of money concept and how to calculate the future and present values. And in the next video, we will have a look how this works in Python. So hope to see you there. Bye. In this video, we will use Python as a calculator, and we will calculate future values. So we are here in a Jupyter notebook, and our task is to calculate the future value of $100 in 1 year when we have an interest rate of 3%. So let's go here into the next cell, and let's type 100 times 1.03. And then let's run the cell here. And we get $103, so that's the future value. And it actually doesn't matter if we have here white spaces or not. So this works as well. And also here, or we could have 2 white spaces here, so that's no problem. And we can also have an alternative intuition. So in 1 year, we still have the principal of $100, plus actually the interest that we can earn in 1 year on the $100. And the interest is actually 100 times 3%. And of course, we also get here 103. And of course, corresponding to the formula that we learned in the last video, we can also calculate 100 times 1 plus the interest rate. So let's do this here. 100 times, and then we have 1 plus 0.03. So this of course works as well, so we can use here brackets. And there's actually one thing that I want to highlight here. So the Python calculator follows the basic algebraic rules. So multiplication or division first, and then addition and subtraction. So let's have a look here. Let's make the same calculation here, and I copy here the code and paste it into the next line. And let's assume that we forgot the brackets here. So typically multiplication and division first. And by having the code here, first of all, Python calculates 100 times 1. And then it adds 0.03, and this gives us here not 103, but 100.03, so that's incorrect here. So same as with any other calculator, we have to set here some brackets. And now let's go to the 3 years case. And here we have to calculate the future value of $100 in 3 years at an interest rate of 3% per year. And therefore we can calculate here 100 times 1.03. So that's the value in 1 year. And then we multiply this with 1.03 again. So that's the value in 2 years. And finally, we also multiply it again with 1.03, and we get the future value in 3 years. So that's the long version, but we can also calculate 100 times 1.03 and then to the power of 3. So we have 3 years, and we can actually calculate to the power by having 2 times the star symbol here. So this works here, and again we have 109.27. Alright, thanks for watching, and I'll see you also in the next video. Bye! In this video we are going to calculate present values with Python. So here we have our first problem, and let's assume that we need to spend $110 in 1 year. How much US dollars do we have to save today at an interest rate of 4.5% to have $110 in 1 year? And we've already learned that we can calculate the present values by discounting future values. So here we have the future value 110. And then we divide 110 by 1.045. And we can actually perform divisions with a forward slash. So this is 110 divided by 1.045. And this gives us 105.26. And of course, you can also make this more explicit. So let's copy here the code and let's paste. And let's create some brackets here. And instead of having 1.045, we have 1 plus the interest rate of 0.045. And let's close the brackets here. So this is of course the same. And of course also here we have to follow the rule multiplication and division first, and then addition and subtraction. So let's copy here the code. And let's assume that we forgot the brackets here. Then of course we get a different result, which is incorrect, so 110.045. And now let's come to the second problem. So here we have to calculate the present value over 3 years. So we have the future value of 110, and we have to discount the future value by 3 periods. So that's discounting over 3 periods with an interest rate of 4.5%, and we get here the present value of 96.39. And also here there's a short version of doing this, so let's copy it here. And we can actually take here the power of 3, so 1.045 to the power of 3 years. And of course this gives the same result here. Alright, thanks for watching, and I'll see you also in the next video. Bye! In the last lectures we calculated future values and present values. And actually in our formulas there's another variable, it's the interest rate. And in this video we will calculate interest rates and also stock returns. And let's have a look at an example here. So here we have, today we receive the offer to deposit $90 in a savings account, getting back $93.5 in 1 year. And we can also have multi-periods, so we can deposit $90 and get back 93.5 in 3 years. And the question would be, what is the applicable interest rate here? And the calculation is pretty straightforward, so we can rearrange the formulas that we already know. And we can rearrange them for the interest rate R. So R is equal to the future value divided by the present value to the power of 1 divided by n. And n is the number of periods, and then minus 1. So let's solve the problems here. And first of all, we deposit $90. And 1 year later, we have 93.5. And actually, the applicable interest rate is here 3.89%. And this is here actually the discounting or compounding factor. So it's 1 plus the interest rate. And let's also have a look here at the calculation. So this is the applicable interest rate, 3.89%. And now let's also have a look at the multi-period case. So we have $90 in T0. And after 3 years, we have 93.5. And the applicable interest rate here is 1.28%. And the discounting or compounding factor is 1 plus the interest rate. So these were interest rates that we can get from a bank, for example. And now let's go to stock returns. So this is a similar concept actually. And let's have a look at an example. So 1 year ago, we invested $50 in a stock. And this stock is now worth $56.5. And the question is now, what is the period return that the stock generated? And this is here the formula. So R is the period return, and we can calculate the period return by dividing the price at the timestamp t plus 1 divided by the price at timestamp t minus 1. So that's the price return of a stock. But typically there are two sources of income when investing into stocks. So we have the price return, which is simply the price increase. And second, we have dividend payments. So typically companies, and in particular more mature companies, pay dividends, for example, quarterly or annually. And let's have a look at an example here. So 1 year ago, we invested $50 in a stock that recently paid a dividend of $2. And the stock is now worth $56.5. So let's have a look at the formula. And we have actually R, now the total return. And actually we can split up the total return into, first of all, the price return. So this is nothing new. And the dividend yield, which is actually the dividend payment at timestamp t plus 1 divided by the price at timestamp t. So that's the dividend yield. And in total, we have here the total return. And typically, the total return is a better metric to measure performance of a stock. So price return, as I said, is only one source. And by having the total return, we can also compare companies or stocks with different dividend payout policies. So that's the formula here. And R is here the period return in terms of total return. And actually, when calculating stock returns, so typically the period is either annual, or we can also calculate monthly returns, weekly returns, or also daily returns. So this depends on the purpose of our calculations and analysis. And in the next lecture, we will exercise this and calculate interest rates and also returns with Python. So hope to see you also there. Bye. In this video, we are going to calculate interest rates and returns. And here in our first example, we receive the offer to deposit $90 in a savings account, and we get back $93.5 in 1 year. And the question is now, what is here the applicable interest rate? And there are actually two options how to calculate this. And corresponding to the formula that we learned in the last lecture, we can calculate the future value divided by the present value minus 1. And this gives us here the interest rate of 3.89%. So it's here 0.0389, but we can also get this in percentage terms by multiplying it with 100. So we can do this, of course. And here we have 3.89%. And actually the second option is to first of all calculate the interest portion. So in 1 year we actually earn an interest of $3.5, and then we have to divide the interest by the initial price or value. So it's here 90, the present value. And we get here the same result, of course, 3.89%. And now let's come to the multi-period case. So the numbers here are the same. We deposit $90 and we get back $93.5 after 3 years. And the question is, what is the applicable per annum interest rate? And again, we divide the future value by the present value. And then we have to the power of 1 divided by the number of periods. And in this example, it's 3. And finally, we also deduct 1. And we actually get here a per annum interest rate of 1.28%. And we can also double check this result. So starting from the present value 90, we can multiply it with 1 plus the interest rate to the power of 3. And then we should actually get the future value of $93.5 US. And of course, this is correct here. All right, coming now to stock returns. And 1 year ago, we invested $50 in a stock that is worth $56.5. So obviously, we have here a price return. So the price increased by $6.5 US. And the return is simply the price of today divided by the price 1 year ago minus 1. So we get here a price return for the 1 year period of 13%. And finally, if a company or a stock also pays dividends, it might be better to calculate the total return, which includes dividend payments. So we not only have here $56.5 as a value of our stock, but we also received a dividend payment of 2. So in total, our value is here 58.5. And then we divide our current value by the price 1 year ago, 50, and then we also deduct 1. And this is here the total return of 17%. So we have a total return of 17%, and this consists actually of a price return of 13% and a dividend yield of 4%. So the dividend yield is 2 divided by 50, which is actually 4%. And this is true. Alright, thanks for watching, and I'll see you also in the next video. Bye. This is an introduction to variables in Python and why they are so useful. So we have our initial example here. We invest $100 for 3 years at an interest rate of 3%. And our task is actually to calculate the future value in 3 years. And this is actually nothing new. And we can actually use Python as a calculator and calculate 100 times 1.03 to the power of 3. And by doing so, we get the future value of 109.27. And we can actually see here that we have the value 109.27 here in the output. However, we didn't save the result in memory. And therefore, if we want to get the future value again, or if we want to work with the future value, then we have to calculate it again. So we have to copy here the code, and we have to recode it. And again, here we have the value. So this is pretty inconvenient, and therefore we have variables in Python. And in Python, we can actually save numbers or whatever objects in variables. And actually the statement saving objects in variables is not 100% correct, as we will see in the next lectures. However, I will use this very often throughout the course, as it is more intuitive than how it actually works in the background. So we will see this in the next lecture. But for the time being, now we want to save the result in a variable. And actually we can simply do this by selecting or choosing a variable. And actually a variable can be everything. So here we have a future value, and we can simply type future value, so FV. And then we have to code an equal sign. So future value equals 109.27. And let's run the cell here. So you can see here that we do not get any output here. So we calculated the future value and we actually saved the future value in the variable fv. And then we can actually get the value that is stored in fv by simply having here fv, and then we run the cell. And by doing so, we can get here the saved value, 109.27. So we can actually save the result of our calculation by assigning it to a variable fv with an equal sign. And there's one thing that you should keep in mind here. So let's copy it again here. And let's put the calculation on the left-hand side. Then we have the equal sign. And let's, for example, choose another variable, maybe a future value 2. And let's try to run the cell here. And this does actually not work. So saving numbers or objects in Python in a variable only works in this format. So you have here the equal sign, and on the right-hand side, here should be the value or the object that you want to store or save. And on the left-hand side of the equal sign, there you have the variable. And of course, we are not limited to save only here the output in a variable. So we can also save the inputs of our calculation in variables. And for example, we have here the present value 100. Then we also have the interest rate of 3%, and we can save it in the variable r. And finally, we have the number of periods. So we have 3 years, and we can save it, for example, in the variable n. And now we can run the cell. And by doing so, we actually saved here the values in the corresponding variables. And we can get the values back by simply running the cell here. For example, present value gives us 100. Then here we have the interest rate is 3%, and also n, the number of periods, is 3 here. And now we can calculate the future value again. And instead of using here the numbers, we can also use the variables. So for example, we can have here present value times 1 plus r, and then to the power of n. And this should give actually the future value, so 109.27. And again, we can also save here the result in the variable fv. So let's copy here the code. And on the left-hand side, we have here future value equals. And now we can get the future value again by simply running the cell here, future value, and it's 109.27. All right, thanks for watching, and I'll see you also in the next video. Bye. This is a short excursus on inline comments. Sometimes it might be the case that you want to add a comment to your code that is just a comment and not part of the actual code. For instance, to enhance readability for others. And in Python, this is not a problem. So a comment starts with a hash character. So let's add here a comment, and let's code hash. And here you can see that it is getting blue. And then you can write your comment, for instance, calculation the future value. And actually you don't need a new line for it. So you can also add a comment here on the right-hand side of the actual code. So a comment starts with a hash character and ends at the end of a physical line. So here, for example. And once you include a hash character to a line, all following characters are part of the comment and not part of the actual code. So for instance, it wouldn't work if you include the comment here on the left-hand side. And by doing so, you actually comment out the whole coding line. So again, once you include a hash character, then all of the following characters are part of the comment. And for instance, it might be useful to comment out a line or a code that results in an error message, for instance here. And let's have another example. So for instance here, this is the present value. Then this is the interest rate and so on. And finally, there's another very helpful application of comments. So sometimes you want to run only parts or fractions of a code and play around with the code. And instead of copying and pasting and deleting code fragments, you can simply cross out the parts of the code. So for instance here, we have present value times 1 plus r to the power of n. And if you are not sure to which object PV is referencing or pointing to, then you can cross out the following code and just run PV. So first of all, we have to define PV, of course. So this is 100, and let's delete here the hash character. And then, for instance, we can calculate the future value in 1 year by crossing out to the power of n. And this gives 103. And finally, we can delete here the comment. And now we calculate the present value in 3 years. So this is pretty helpful, and I will use this a lot in the whole course. So thanks for watching, and I'll see you also in the next video. Bye. This and the next lecture are more theoretical in nature. However, they are pretty important to understand how Python works in the background and how Python stores variables in memory. So it's really important to understand this to avoid the most frequently made mistakes in Python. So here we have a view on our memory, and actually each memory slot has a memory address. So for example here we have this slot with the memory address 0x1000. So this is only for illustration purposes. And now let's assume that we have the following Python code. So we store the number 0.03, so 3% in the variable r, so that's the interest rate. And by doing so, we create actually the object 0.03, so this is a number. And this object is getting stored in memory, for example, here in the slot with the address 0x1000. And then we have our variable r. And actually the variable r is referencing or pointing to the object stored in the memory address 0x1000. So actually variables are memory references. And whenever we use r in our Python code, then Python searches for the object that r is referencing to and uses actually the object here. So in this example, 3%. So actually the statement we save 3% and the variable r is not 100% correct. So either the variable is referencing or pointing to the object stored in a memory address, or we could also say that the object 0.03 is assigned to the variable r. Alright, thanks for watching, and I'll see you also in the next video. Bye. In this video I will show you in more detail how objects in Python are stored in memory and how variables are assigned and reassigned. So this is a pretty important lecture, and you should make sure that you understand the mechanics in the background to avoid the most frequently made mistakes when working with Python. So we have here two interest rates. We have 3% and 4%, and we save the objects here, and we assign 3% to the variable r1 and 4% to the variable r2. And then we can check again that r1 is referencing to 3% and r2 is referencing to 4%. So this is nothing new. And now in the next step we can say that r1 is equal to r2. So let's run the cell. And actually Python is now verifying that r2 is referencing to the object 4%. And it actually assigns 4% also to the variable r1. So r1 should now be 4%. So let's check this. And of course r2 is still also 4%. And now in the next step, let's change r2 to 5%. So it's actually no surprise that r2 is now referencing to 5%. However, the question is now, is r1 referencing to 4% or to 5%? And we can check this. And actually r1 is still referencing to 4%. So now let's have a look how this works in detail in memory. So that's our initial situation. We have two objects. We have 3%, and r1 is pointing or referencing to 3%. And we have the second object, 4%, and the variable r2 is referencing or pointing to the memory address where we have stored 4%. So now let's move on and let's assume that we have the code R1 equals R2. And now actually Python checks in memory to which object R2 is referencing to, and here it's 4%. And then Python changes the reference of R1 from 3% to 4%. So it actually deletes the reference to 3% and it creates a new reference to 4%. And now as a direct consequence, as we have no variable that is pointing or referencing to the object 3%, then Python assumes that the object 3% is no longer needed and it actually drops 3% from memory. Alright, so now let's have the next step and we have the code R2 equals 5%. And here it is really important to understand that we do not change here the object in the memory address 0x1001. So we do not change here the object, but we create a new object, 5%, and we store the new object in a different memory address. So for example, in the memory slot with the address 0x1003. And now Python is simply changing the reference of R2. So initially we had the reference to the object 4%, and this is now deleted, and Python creates a new reference to the object 5%. And as you can see, the reference of the variable R1 did not change, so we still have the reference of R1 to the object 4%. So even if we coded here R1 equals R2, so if we change the reference of R2 afterwards, then R1 is not equal to R2. So R1 is not referencing to the same object now as R2. So now let's move on with another example and let's assume that we change R2. So the new R2 is actually the old R2 plus 0.01. So R2 is now 6%. And also here it's important to understand that we do not change here the object 5%, but we create here a new object 6%. And actually we store the new object in a different memory slot with a different memory address. So here 0x1004. And then Python simply changes the reference of R2 from the object 5% to 6%. And finally, as there is no variable that is pointing or referencing to the object 5%, then Python actually drops the object 5% from memory. Alright. We are now back in our Jupyter notebook and R2 is referencing to 5% and R1 is referencing to 4%. And again, we can say that R1 equals R2. Then we change the reference of R1 and R1 is now 5%. Now the next example we have already seen in the slides. So we can reassign R2 and we can say that R2 is equal to R2 plus 1%. So R2 is referencing currently to 5% plus 1% gives 6%. So we reassign R2 to 6%. And of course, the reference of R1 is still to the object 5%. And at this point, I want to make a short excursus here. So let's assume that we have the interest rate R, and R is 5%. And now let's assume that we want to increase R to 6%. Then this is here the long version. So we reassign R equals R plus 1%. And now we have 6%. But there's also a short version, so we can simply code R plus equals 1%. And by doing so, we actually increase R by 1%. And here we have 7% now. And the same we can also do with a minus sign. So we can decrease R by 2% or 2 percentage points. And we can do this by coding R minus equal 2%. And by doing so, we change R to 5%. Alright, thanks for watching and I'll see you also in the next video. Bye. In this video I will show you some rules and conventions for using variable names. And the high level message is that we are not completely free when we create variables. So variable names must follow certain rules and should follow certain conventions. And so far we have used rather short variable names, for example R for interest rate. And that's of course allowed, and this is perfectly fine. But let's assume that you want to have complete words, for example, interest rate. And here we get an error message, and the reason is that we cannot use the white spaces in variable names. So instead of having white spaces, we should use, for example, underscores. And this works here. Next, our variable names should always start with a lowercase letter. So a variable cannot start with a number. So for example, first interest rate, here our first character is a number 1. So this does actually not work. And also having complete numbers as variables does not work. So 2010 equals 5% does not work. And instead also here we should use underscores. So for example, interest rate in 2010. And here we have underscores as separators. So this works perfectly. Next, we cannot use the so-called Python keywords. So true, for example, is a keyword. And if we try to run the cell here, we get the error message can't assign to keyword. And let's have a look at an overview of the Python keywords. These are the reserved keywords in Python, for example, false, none, true, and, s, and so on. And we will get in touch with most of these keywords somewhere in the course, so there's no need to go into detail here. And the message is here that we cannot use reserved keywords as variable names. So these are the rules that we have to follow, but the variable names should also follow some conventions that have been created by the Python community. And actually by following these conventions, this makes your code easier to read and understand for others. So for example, a variable name should always start with a lowercase letter. And theoretically, you could also start with an underscore. But expressions starting with an underscore is already reserved for other things. So that's clearly not the best convention here or the best solution, but it works. And if we have several words in our variable, so we should always separate the words by an underscore, but we could also use here interest rate without an underscore. And as a next convention, we should only use lowercase letters. So for example, here we have interest rate with an uppercase I and R. And this format is typically used for classes. So this is actually reserved for classes, and it might cause some confusion if you use this here as a variable name, but it works actually. So finally, let's assume that you want to store the interest rate in 2010, 5%. And this is actually here the best practice. So we have lowercase letters separated by an underscore. And also here, the number or the year 2010 is separated here by an underscore. So that's actually the best practice and the convention actually. Thanks for watching, and I'll see you also in the next video. Bye. In this video, I will show you the very first built-in function in Python, the print function. And the print function prints a specified object or value to the screen. So we've already seen that if we calculate the price return of our stock, the result is in the output line. So let's run the cell here, and here in the output line we have 13% as the price return. However, let's calculate the price return and total return in one line. So let's run the cell here. And here we can see that only the result of the very last line here, so the total return, is displayed in the output, so 17%. And actually Python still calculates also the price return, but it's not displayed here in the output line. So in this case and more complex cases, we can use the print function to customize the output that we can see on our screen. So we use here the statement print, and then we open the parentheses, and within the parentheses here we pass our calculation for the price return. And let's run the cell here. And no surprise, we get here the result, 13% price return. And actually with the print function, we not only can display one result or one value, but we can print or display many values. And we can do this by passing here many calculations. So for example, here in this case 2, within the parentheses, and we separate the values by a comma. So let's run the cell here. And here we get the price return and the total return. And we can see here that by default the values are separated by white spaces, but we can also customize this. And actually the print function has one parameter. It's the separator parameter here, sep. And the default argument is actually a white space. But we can also pass here the combination comma white space within quotation marks. And let's run the cell here. So here we get the two values separated by a comma and a white space. So as I said before, sep is a parameter of the print function. And here we have changed the argument for the parameter. And later in this course, we go into the details of functions, parameters, and arguments. But for the time being, it's just sufficient to know that the print function has the parameter separator, and here we can pass actually different arguments. So for example, as a third alternative, we could also pass here \n, and actually a \n stands in coding for new line. So let's run the cell here. And here we print out the price return and the total return in actually different lines, so in a new line here. And finally, let's have a more complex example. So let's assume that our interest rate is 3%, and actually we assign it to the variable r. Then we have our discounting factor or compounding factor, which is 1 plus r. And then we want to print out the intermediate result f. And then finally we want to calculate the future value by multiplying 100 and f. And then finally we print out the future value. And here we can see in our output that we have printed the intermediate result f, and also the final result, the future value of 103. So in later sections with more complex situations, you will definitely get a better understanding when and why to use the print function. So for example, when we use for and while loops, in many cases, it definitely makes sense to print out intermediate results. So thanks for watching, and I'll see you also in the next video. Bye. Hi and welcome to the very first coding exercise. Here you will have the opportunity to practice and master what you have learned in the video lectures. And actually the exercises are not mandatory to follow the course, but I highly recommend doing the exercises as it deepens your understanding, and actually learning by doing is definitely the best way to become an expert. I'm here on my desktop and I've already downloaded the course materials for part 1. So let's have a look here. And here we have the video lecture notebooks for part 1 and also the exercises. So in total we have here 8 exercises in part 1. And now let's open the Anaconda Navigator. And let's select the Jupyter Notebook. And we know that we have stored the course materials file on our desktop, and therefore we select desktop. And this is actually a view on our desktop. And here I can find the course materials part 1 folder. And let's go to exercises and to the very first exercise. Alright, exercise 1 is all about using Python as a calculator for basic time value of money problems. And you should actually use the variables where appropriate. So input values and also final results shall be stored in variables. And here, first of all, you have to calculate the future value. So here in the first coding cell, you should store the input values in variables. Then in the second cell, you have to calculate and store the future value in a variable. And finally, you have to print out the result. And actually here you can check whether your result is correct. So in this case, the correct result is 2631. Next, you have to calculate a present value. And also here you can see the result. Then you have to calculate the per annum compound interest rate. Then question 4, there you have to calculate the price return of a stock. And then also you have to calculate the dividend yield and the total return. And finally, you are asked here to print out the price return, dividend yield, and total return in one single line. Alright, this is coding exercise 1, and I will continue now with the solutions. So if you want to do the coding exercises on your own, then please stop the video now. So in question 1, we have the following situation. We save $2,000 for 7 years at an interest rate of 4%. And here we shall calculate the value of our account in 7 years. And that's actually the future value in 7 years. And first of all, we have some input values, which we should store in variables. So we have the value today, the present value is 2,000. Then we have the number of periods or years, 7. And we have the annual interest rate of 4%. So let's actually store the input values in variables. And then we are asked to calculate and store the future value in another variable. So here we have to follow the future value formula. And actually the future value is the present value times 1 plus r to the power of n. So let's run the cell here and let's store the future value in the variable future value. And finally, let's print out our result. And this is obviously here the correct result. So 2,631. So we saved $2,000 today, and after 7 years, we have $2,631. Next, question 2 is actually the opposite calculation. So we consider to purchase a car in 4 years for $20,000. And the question is now, how many US dollars do we have to save today? So that's the present value to have these $20,000 in 4 years. And we assume that we can save our money at an interest rate of 3.5%. So we have some input values here. We have the future value in 4 years of 20,000. We have 4 years and we have the interest rate of 3.5%. And then we have to rearrange the formula for the present value. And actually we have to discount the future value for 4 periods at an interest rate of 3.5%. So let's run the cell here and let's save the result in the variable present value. And let's have a look. So here we get $17,428 that we have to save today in order to get 20,000 in 4 years. In the next question, we have to rearrange the formula for the compound interest rate R. So Bank B offers us to save $10,000 today, and we get back $15,000 in 10 years. And here we should calculate the per annum interest rate or compound interest rate. And we should compare this interest rate to the interest rate that Bank A offers, so 4.5% per year. And which offer should we accept? So actually the higher one, and let's have a look. So today we save 10,000, that's the present value. Then in 10 years we have 15,000 and we have 10 years. And if we rearrange for the interest rate, then we get the future value divided by the present value to the power of 1 divided by 10 years, and then finally minus 1. And here we get the per annum compound interest rate of 4.14%. So this is less than Bank A offers. So Bank A offers 4.5%, and therefore we should accept the Bank A's offer. Now let's come to stock and stock returns. And 1 year ago we invested $976 in the ABC stock. And then 1 year later, we received a $40 dividend payment, and the current value is $1,053. And first of all, we shall calculate the price return. So we have the price 1 year ago, 976, and we have the price 1 year later, today, 1,053. And the price return actually does not take into account the dividend payment, and is simply the price today divided by the price 1 year ago minus 1. So we get a name error here, and it says P1 is not defined because we didn't run the cell here and we didn't create the variable P1. So let's first of all run the cell here, and by doing so we actually create the 3 variables here. So now let's run again. And let's check the price return. And we get here 7.89%. Here in question 5, we have to calculate the dividend yield and the total return for ABC. So the dividend yield is simply the dividend payment divided by the price 1 year ago. So 40 divided by 976, and this gives a dividend yield of 4.1%. And then finally, the total return is the price return plus the dividend yield. So we saved our results here in price return and dividend yield. And we get here 11.98%. And finally, we can also print out all results. So the price return, the dividend yield, and the total return in one single line, separated by commas. And we can do this with the print function. And then we can pass the values or the variables that we want to print out. So the price return, the dividend yield, and the total return. And there is the parameter sep, where we can define how the elements are separated in the printout. And we have to pass this within quotation marks as a string. And we want to separate by a comma, so comma white space. And let's have a look. So here we get the price return of 7.8%, comma, then we have the dividend yield of 4.1%, and finally the total return. Alright, this was coding exercise 1. I hope you had fun, and see you also in the next exercise. Bye. Hi and welcome to this section. So far we had time value of money problems with only one cash flow, but typically investment projects, loans or retirement plans have many cash flows. And in this section we will learn how to calculate future values and present values for projects with many cash flows. So let's have a look at an example here. So we have today $100 US in our savings account, and we save another $10 in 1 year, $20 in 2 years, $50 in 3 years, $30 in 4 years, and $25 in 5 years. So each payment is at the end of the period, so at the year end. And the question is now, what is the future value of our savings account after 5 years? And we assume an interest rate of 3% per year. So let's have a look at the formula. And this looks quite complicated. But in the end, we have to calculate for each and every cash flow the future value of the cash flow in 5 years. So let's have a look how it works. And it's always helpful to have here a timeline with timestamps and cash flows. So for example, we have today $100, then in 1 year we pay $10 and so on. And finally, at the end of year 5, we pay $25 into our account. And to get the future value of our account, we have to calculate the future value for all cash flows. So we start with the current value of our account, $100. And actually, we have to compound $100 by 5 periods with an interest rate of 3%. And this gives a future value of 115.93. And actually, the same thing we are doing now for all of the other cash flows. So we compound the next cash flows by 4 periods, and we get 11.26. Then we compound the cash flow in year 2 by 3 periods, and so on. And actually the final cash flow in year 5, it's 25, so we do not have to compound this. And finally, the future value of our complete account is actually here the sum of the future values. So let's have a look at the result of our calculations here. And finally, we end up with a future value of 257.98. And actually, we can do the same calculation here also in Python. So we are here in the Jupyter notebook, and here we have the same task actually. And actually, we can calculate the future value by compounding 100 for 5 periods, then 10 for 4 periods, and so on. So we save here the result in the variable future value. And also here we have the final result of 257.98. And if you think that coding or calculating this in this manner is not really efficient, then you are right. So there are more efficient ways to do this in Python. And we are starting right now in the next lecture to discover more efficient ways to do it. So thanks for watching, and I'll see you also in the next video. Bye. This is an introduction to Python lists, and lists are containers where we can store many other objects like numbers. So here in our example we have a savings plan with 6 cash flows, and theoretically we can store these 6 numbers in 6 different variables, so from t0 till t5. And this works, but it's actually not the best way how to do it. So we can run the cell here, and we can create here these 6 variables, and we can actually call here one variable, for example t0, and of course t0 is referencing to 100. However, it's better to store many objects in a collection or a container, and Python and associated libraries provide several containers or collections, and one of the most frequently used collection is the list. And actually we can create a list by opening square brackets. And then within the square brackets, we can pass our objects separated by commas. So our very first cash flow is 100, comma, then we have 10, then we have 20, and then 50, 30, and 25. So let's run the cell here. And here we can see our list with the 6 elements. And actually it doesn't matter if we have here white spaces between the commas. So we can also delete this here. So this works as well. And by default here in the output we can see that we have element, comma, white space, and then the next element. But we do not have to code this exactly in this manner. So we can also create a white space here, and it still works. And finally, we can also assign our list to a variable. So let's copy it here and let's paste it. And let's assume that the variable name is cash flows, CF. So the variable CF is now referencing to our list. And of course, we can also get our list here by running here CF. And again, here we have our list with our 6 cash flows. Alright, thanks for watching, and I'll see you also in the next video. Bye. In the last video we have created the list CF, and we have stored our 6 cash flows in this list. And the question is now, how can we get or how can we access single elements of our list CF? And this process is also called indexing. And there are actually 2 ways to do it. So first of all we have zero-based indexing, which is one of the most important and fundamental concepts, not only in Python, but also in other programming languages. And we have a negative indexing. So let's have a look at zero-based indexing first. And actually lists are also so-called sequences, as the sequence of the element matter. So the sequence is not random, and they are so-called index positions. And the very first element, or the most left an element, is at index position 0. It's really important to understand that we start with index position 0 and not 1. Therefore, it's called zero-based indexing. And consequently, the second element is at index position 1. Then the third element at index position 2, and so on. Now the second alternative is negative indexing, and also here we have our list and we have index positions. And with the negative indexing, the very last element, or the most right-hand element, is at index position -1, and the second last element is at index position -2, and so on. So finally our very first element is at index position -6. Now we know that we have index positions, so how can we index our list? And let's have an example here. So we want to get the very first element 100, and therefore we have to code CF, and then we have to open square brackets and pass the index position of the very first element. So in this example it's the index position 0, and we get the element 100. So that's zero-based indexing. And let's also have a look at negative indexing. So let's assume that we want to get the second last element, 30, and we can actually access the second last element with negative indexing. So we code the CF, then we open square brackets, and we pass the negative index position -2, and by doing so we get here 30. Alright, I think we have to see this also in action, so hope to see you also in the next video. Bye. Alright, in this video I will show you how indexing of lists works live in action. And here we have our list with our 6 cash flows. And actually we assign the variable CF. And then we can index our list. And for example, let's assume that you want to get the very first cash flow, 100, at index position 0. Then we can pass here 0 inside the square brackets. And by doing so we get 100. And we can also index for the second element 10 at index position 1 and the third element at index position 2. And of course we can also get the fifth element at index position 4. So let's count here. So here we have index position 0, 1, 2, 3 and 4. So we should get 30 here. And that's correct. So this is zero-based indexing, and now let's come to negative indexing. And let's assume that you want to get the very last element, and in this case it's 25. Then we can pass the index position -1 within the square brackets here, and we get 25. And we can also get the second last element, it's 30 with -2. And we can also get the element at index position -5. So let's count here. -1, -2, -3, -4, -5. It should be 10. And that's correct here. And now let's again try to calculate the future value of our cash flows. And we create a second list n with the timestamps. So we have the first cash flow, 100, at timestamp 0, and then 1, 2, 3, 4, and 5. So we have 2 lists here, n and CF, and we have our compounding or discounting factor 1.03. So we have 3% per year as interest rate. And then we can actually calculate the future value by actually indexing the lists CF and N. So actually we have our very first cash flow at index position 0, it's 100. And we have to compound 100 by 5 periods. So we multiply by f to the power of n and the very last element, so 5. So here we compound 100 by 5 periods. Then we have the second element at index position 1, it's 10. And we compound 10 by actually 4 periods and so on. So let's run the cell here. And no surprise, also here we get the future value of 257.98. And you're actually right that also this approach here is not really efficient. And therefore, in the next video, I will introduce for loops. So hope to see you there. Bye. In this video, you will learn how to iterate over lists with a for loop. So what does it mean? With a for loop, you can go through all elements in a list from the first element to the last element, and you can define an action that you want to take on each element and on each loop actually. And options are unlimited here. So for example, you can simply print out each and every element, or you can multiply each element by 2. So we could say that for loops enable element-wise operations, because they allow to iterate over a sequence or a collection like lists. And therefore a list is also called an iterable because we can iterate over the list. So let's see how it works in action. And let's assume we want to print out each and every cash flow in the list cash flow from the first to the last element. So let's first of all create the list here. And now let's initiate the for loop. And we actually have the keyword for. So you can see here it turns green, and that's a signal that this is a keyword that, for example, we shouldn't use as a variable name. And then we can code for element in our list CF, and then we need to code here a colon and press the enter key. And you can see here that Python makes automatically an indent here. And this is really important that we have this indent here. And then here in the next line, we can define the action that we want to take on each and every element. And here in this example, we want to print out each and every element. So let's run the cell here. And here we have printed out the 100, 10, 20, 50, 30, and 25. And as I said before, so it's pretty important to have the indent here. So if we actually delete the indent here, then this does not work actually. So expected an indented block. And we can again create the block here or the indent with the tab key. So now it works again. So that's the for statement with the keywords for and in. And we iterate over the list CF. And actually on each loop we call the next element. So for example, the very first one, then the second one, and so on. And we actually put the next element in the loop variable element. So this is flexible here. So we can select any loop variable that we want to have. And I can show you this in the next coding cells here. So let's go down here. And instead of having the loop variable element, we can also say for I in CF, print I. So this is no problem. This also works. And even we can define the loop variable underscore. So for underscore in CF, print underscore. So this is completely flexible. Of course, we shouldn't use any Python keywords. And having understood the concept of a for loop, now, for example, we can actually count the number of cash flows that we have in our list. So here, obviously, it's 6, but we can explicitly count them. And for example, we can define here a variable and set the variable to 0. And then we initiate a for loop. So for each element in our list cash flow, we want to increment or increase the count by 1. And then we want to print count. So let's run the cell here. So here we have in the very first loop, we have 1. Then in the second loop, we have 2 and so on. And finally, we end up with a count of 6. So that's the for statement here. And these two lines are actually the actions. So we increment count by 1 in each and every loop. And also we print out the current count on each and every loop. But actually we can also exclude the print statement from the loop. And therefore we can delete the increment. And by doing so, we actually exclude here the printing from the for loop. And actually we only print out the variable count at the very end after the very last loop. So let's have a look here. And here we have 6. So our list cash flow contains 6 elements. And of course, there's also a simpler way to do it. And we have the built-in function length. And here we can pass actually our list cash flows. So we have to open here the parentheses and we pass here cash flows to the length function. And of course, this gives the very same result. So we have here in total 6 elements on our cash flow list. And next we can also take the sum over all elements. So how many US dollar do we save over the 5 years period? And here I do not mean the future value that we have after 5 years, but simply the nominal amounts that we pay into our savings account. And also here we can do this with a for loop. And actually we create a variable total and the initial value is 0. And then we iterate over the cash flow list. And for each element or for each loop in the cash flow list, we increment the variable total by the cash flow. So for example, the very first cash flow is 100. And in the first loop, we get the 100. Then the second element is actually here, it's 10. So we increment total by 10 and have 110. And again, here we have the print statement inside the for loop. So let's run the cell here. And here we get actually the intermediate results and also the final result. So the intermediate result in the first loop is 100, then 110, 130, and so on. And the final result is 235. And also here we can exclude the print statement from the loop, and we can only print the very last loop or result, so the total sum over all cash flows. And it's 235. And also here we have a Python built-in function, so it's the sum function, and we can pass our cash flow list inside the parentheses, and this gives us, of course, the same result, 235. And last but not least, so let's assume that we have our cash flows here in US dollar, and we want to convert each and every cash flow into euro at a conversion rate of 1.12. So we have 1.12 US dollar per 1 euro. And again, we have here our cash flow list. And then we iterate over the list. And for each and every element, we actually divide each element, which is a cash flow in US dollar, by 1.12. And by doing so, we calculate the corresponding euro cash flow. And we print out the euro cash flow. So, for example, here we have for the cash flow $100, the corresponding euro cash flow 89.28, and so on. Alright, thanks for watching, and I'll see you also in the next video. Bye. In this video, you will learn how to use the very helpful range function and how to create and work with a range object. So a range object is another iterable that we can iterate over. And a range object actually can produce a sequence of integers from a predefined start to a predefined stop in a predefined steps actually. So in simple words, you can create all integers, for example, from 0 till 9 or from 1000 till 2000. So we have the function range, and inside the parentheses we can, for example, pass 10. And by doing so, we create a range object 0, 10. And we will see in a minute which numbers we can create with this range object. But at this point, it's important to understand that a range object is an iterable like a list, but it's not a collection or a sequence, as the elements haven't been produced or stored in memory yet. But a range object can produce the elements when called. So the question is now, how can we call the elements of a range object and store the elements in memory? And one way would be by creating a list with the list function. So the list function is another Python built-in function. And here we can pass our range object within the parentheses. And let's simply run the cell here. So we passed the range object 0, 10. And obviously we created the numbers or the integers from 0 till 9. So by default, the start is at 0 inclusive, and the end, for example, if we pass here 10, at the end exclusive. So 10 is exclusive here, and we end here at 9, and the default step is 1. So we have here steps of 1. However, we can also change start and the steps. So for example, we can explicitly say that the start should be 1. And the end is 11 exclusive, so 1 inclusive and 11 exclusive. And this gives us here a list from 1 till 10. And finally, in the third position, we can also define the step size. So by default, it's 1, but we can also explicitly set this to 2. Let's have a look here. So here we have the numbers starting from 1. And we have a step of 2, so 3, 5, 7, and 9. So with the range function, we create a range object. And actually we can, each and every object, no matter if it's a number or a range object or whatever, we can save an object in memory and assign it to a variable. So for example here, we have the numbers from 0 till 5 inclusive. So these are the timestamps of our cash flows. And we can save those in the variable n. So here we have a range object 0, 6. So this includes 0, 1, 2, 3, 4, and 5. And actually we can also index a range object. So we can select the second element at index position 1. And in this example it's 1. And before I said that a range object is another iterable that we can iterate over. So we can use here a for loop. So for each element in range 6, we can print the element. And consequently, we get the elements 0, 1, 2, 3, 4, and 5. And of course, we can also define a more complex action here. So we simply print out all elements here. But we can also calculate and print out all elements to the power of 2. And this gives us 0, 1, 4, 9, 16, and 25. So finally, you could ask, what are the benefits of a range object compared to a list? And let's assume that we have 1 million iterations. Then one option could be that we create a list with 1 million integers. And we iterate over the list with all 1 million elements in memory. Or we can iterate over the range object, and with a range object, we never store all 1 million elements at the same time. So on each and every loop, we only produce the respective number for that loop. And that's of course more memory efficient. So with a list, we store each and every element of the list. So in our example, 1 million elements at the same time in our memory. Alright, thanks for watching, and I'll see you also in the next video. Bye! In this video, we will use lists and for loops to calculate present values and future values for projects with many cash flows. So here in the first question, we shall calculate the future value of our savings account in 5 years, given an interest rate of 3% and the following cash flows here. So that's the solution for our problem here. And basically there are two lists that we have to iterate over in a for loop. So we have the list with the cash flows, starting with 100, 10, 20, and so on. And second, we have the compounding period, starting from 5 years for the first cash flow and ending at 0 for the very last cash flow in year 5. So let's go back to our Jupyter notebook and let's start coding. And first of all, we are creating the cash flow list with the 6 cash flows. And then we need to create a list with the compounding periods. And first of all, we create here the list n. And actually, we have here a range until 6 excluding from 0. So that's n, but actually we need the reverse order. And we can actually reverse the order with the following code. So this is a special case of slicing lists. And later on in this course, we will have a deep dive into slicing lists. So let's simply run the cell. And by doing so, we are actually reversing the order, starting now from 5 until 0. So we need to compound 100 by 5 periods and 10 by 4 periods and so on. Then we have our compounding factor of 1.03, which is 1 plus the interest rate. And then we can actually calculate the future value. And we create the variable future value. And initially we have a value of 0. And then we iterate over all cash flows. And actually we add the future value of each and every cash flow to the future value here. Now for I in range 6, so for each and every cash flow, we increase or increment the future value by actually the cash flow times the compounding factor to the power of the compounding period. So let's have a look at the very first loop and the first iteration. So we have I equals 0. And we actually index the cash flow list for the index position 0, which is 100 here. And then we multiply it with the compounding factor to the power of the very first element in the list n, which is 5 here. And in this way, we are doing this for all cash flows. And we are actually incrementing the future value. So let's run the cell here. And we actually print out intermediate results. So the future value of our first cash flow is 115. Then the sum of the future values for the first 2 elements are 127 and so on. And finally, we end up with a future value of 257. So after 5 years, we have $257.98 in our savings account. And of course, instead of printing all intermediate results, we can also only print out the final result by actually removing the print statement from the for loop here. So here we have our final result of 257. And now let's come to present values and let's have a look here at the example. So today we agree with a bank on a payout plan that guarantees payouts of $50 in 1 year, $60 in 2 years, $70 in 3 years, $80 in 4 years, and $100 in 5 years. And the question is now that we have to calculate the funding amount or the present value of these cash flows that we need to pay into the payout plan. And let's assume that the applicable interest rate is 4% per year. So in simple words, the question is here, how many US dollars do we have to save today that we get the following payout plan here? And actually, this is an example to calculate present values for projects with many cash flows. And also here we have a formula. So actually, essentially, we have to calculate for each and every cash flow the present value, and then we have to sum up the present value of all cash flows. So let's have a look at the solution here. And again, it might make sense to draw here a timeline. And first of all, we have the cash flow in 1 year. And actually, we have to discount this cash flow over 1 period at an interest rate of 4. And we get here the present value of 48.08. And the same we can do also for the other cash flows. So we have to discount the cash flow in year 2 by actually 2 years. And the cash flow after 3 years by 3 periods. And so on. And finally, we have to take the sum over all present values. And let's have a look at the final solution here. So we get a present value of 316.36. So today we have to save 316.36 US dollars in our savings account in order to get the following payout plans. So 50, 60, 70, 80, and 100. All right, now let's go back to our Jupyter notebook and let's see this in action here. And again, we are creating the cash flow list with the cash flows. So we have 50 in 1 year, 60 in 2 years, and so on. And we have the discounting factor of 1.04. And then we create the variable present value, and the initial value is 0. And in total, we have here 5 cash flows, so we have 5 loops. So for I in range 5, and in each and every loop, we increment the present value by the present value of the respective cash flow. So let's have a look how this works in the first loop. So we have I equals 0. Then we take the very first element at index position 0, it's 50, and divide it by f to the power of I plus 1, which is actually here 1. So here we have to increment I by 1 in each and every loop to get actually the discounting period. And also here we can print the intermediate results. So the present value of the very first payout, 50, is 48. And in total, the present value of all payouts is 316. So we have to fund our savings plan, our savings account today with 316 to get the guaranteed payout plan here. All right, thanks for watching, and I'll see you also in the next video. Bye. In the last lecture, we have calculated the present value of our payout plan that we arranged with a bank. And we calculated a present value of all payouts of 316.36. So that's today's value of all benefits that we receive in the future. And at the same time, that is also the funding amount or saving amount that we have to pay into our plan today. And I0 stands for the investment today. And we have a negative sign here. So this is a cash outflow today. And in the future, we have positive cash inflows. In this particular case, we have the situation that the present value of all inflows is equal to the initial investment. So if we rearrange this, we can also say that the initial investment, which is negative, plus the present value of all inflows is 0. And this is exactly the net present value, or short NPV. So net because we deducted the initial investment from the present value of positive inflows. And here in this example, we have a net present value of 0. And the reason is that here we have a structured bank product. So the savings amount or the initial investment was calculated based on the positive inflows. However, that is not the standard case in real world. So let's have a look at a real world scenario and a real world investment example. So here we have the XYZ company, and it evaluates to buy an additional machine that will increase future profits or cash flows by $20 in the first year, $50 in the second year, and so on. And the additional machine costs $200, so that's the investment today or in T0. And our task is now to calculate the project's net present value and evaluate whether the company should pursue the project. And actually XYZ's required rate of return, or the cost of capital, is 6% per year. So later on we will have a more detailed look here on required rate of return or cost of capital. But first of all, let's have a look at the formula. And this is actually nothing new. So here we have the present value of all inflows. And here we have the initial investment, which is negative. So net present value is equal to the initial investment negative plus the present value of future inflows. And here we have R, which is the required rate of return or the cost of capital of the company. And typically in those real-world investment projects, the initial investment is not equal to the present value of positive inflows. So we have a net present value that is unequal to 0. So either we have a positive net present value or we have a negative net present value. And actually the most important question for each and every project is now, should we accept a project or should we reject a project? And the decision rule is pretty simple. So if the net present value of a project is positive, then we should accept the project and pursue the project. And if the net present value is negative, then we should reject the project. And I also want to give you an interpretation of net present value. So typically when we pursue or accept a project with a positive net present value, then theoretically today's company value should increase by the net present value of the additional project. And in total we can say that the total company value is actually the sum of the net present values of all projects. So this might be a bit theoretical, but this is actually the interpretation for a total company value, or actually the sources of a company value. So it's the sum of all projects' net present values. And we've already seen in our formula that we do not have an interest rate, but a required rate of return or cost of capital. So here in red. And I also want to give you a short intuition on the required rate of return of a company. So the required rate of return is actually the expected return of comparable or alternative projects. Or we could also say the return of the second best or next opportunity or project. So let's have an example here in private life. And let's assume that a bank offers you an interest rate of 2.5% on the savings account. However, on your existing account with your existing bank, you already get an interest rate of 4%. So this 4% is actually the next best opportunity or alternative. And it's in a way your opportunity costs. So you would only change to a new bank and to a new savings account if it provides a higher interest rate than your existing savings account. So in this example, you probably wouldn't change the bank and the savings account if you get only 2.5% instead of 4%. And there's also a second intuition for the required rate of return. So typically the initial capital outflow, I0, has to be funded, and a company is typically funded with debt. So we have either bank financing or the company issues bonds to bondholders. And the fixed interest rate is then actually here the cost of debt. So it might be 4% or 5% or whatever. And second, we have also the cost of equity. So that's the required return by the shareholders. So typically, of course, a company is not required to pay fixed interest or dividends to shareholders, but nevertheless, shareholders require a return. And later on in this course, we have a deep dive into required equity returns or forecasting equity returns. But for the time being here, it's sufficient to know that a company calculates with the weighted average cost of capital to fund a capital outflow, and this is also called the WACC, so weighted average cost of capital. And let's also have a short private life example. So let's assume a friend asks you to lend him $1,000 for 1 year, and actually you do not have the $1,000. And before you can do this, you have to go to your bank and also borrow the money from the bank at, for example, an interest rate of 3%. Then this is actually your cost to fund the capital outflow to your friend. And if your friend offers you an interest rate of only 2%, and you have the cost of funding of 3%, then obviously this is not a good deal for you. So this will definitely result in a negative net present value for this project here. All right, that was the theory, and in the next video we will actually calculate and code the net present value with Python. So hope to see you there. Bye. Alright, we are going to calculate now the net present value for XYZ's investment project. And we create here a list with all cash flows, starting with the initial outflow in T0. So today it's minus 200. And then we have positive inflows in the next years. And we also have the discounting factor of 1.06, which is 1 plus the required rate of return or cost of capital of 6%. And then again, we create the variable NPV, which is initially 0. And then we iterate over the cash flow list. So let's have a look at the very first iteration. And here we have I equals 0. So we increment the net present value by the very first element at index position 0, so minus 200, and 200 discounted by 0 periods, so we have minus 200 again. Then next in 1 year we have a positive inflow of 20, and we discount 20 by 1 period, and so on. And finally we print out the final net present value of our project. And it is 38.71, so the net present value is positive, and we should actually accept and pursue the project. And the question is now, would your conclusion change with a purchase price of $250 instead of $200? And actually we can change elements in a list. So we can here index or select the very first element, minus 200, and we can assign actually a new value, minus 250. So later on in this course, we will also have a deeper look how to change and add and also remove values from lists. So this is here a short outlook, and let's do this. And let's have a look again at our cash flow list. So now here we have minus 250. And actually now we rerun here the for loop. And let's calculate again the net present value. And now we have here a net present value of minus 11.28. So the net present value is negative, and therefore we should reject the project here. And the intuition in this case is that the return from the project does actually not cover capital costs. So the capital costs are 6% and having a negative net present value. So we do not cover here the capital costs. Or to have another intuition, so here we should reject the project and pursue the second best alternative, which should give us around 6% here. Alright, thanks for watching, and I'll see you also in the next video. Bye. Welcome to the second coding exercise. We are here on the Jupyter dashboard, and we know that our course materials are located on the desktop. And here we can see course materials part 1. And we go to exercises and select exercise 2. Exercise 2 is all about lists, for loops, and time value of money problems with many cash flows. And therefore, first of all, here we have a savings plan with some cash flows. And we should store the cash flows in a list. And second, we have to index the list for some elements. So today's saving or the saving in year 3 and so on. Then we shall iterate over the list and print each and every element. Then next we have to calculate the sum over all cash flows. And here we should use a for loop. And then question 5, we should do the same, but instead of using a for loop, we have to use a built-in function for the sum, but also for the length. Next, we have to create a range object and print all integers from 0 till 100. And then we create a list with all timestamps of our savings plan from 0 till 6. And we have to use a range object for this. And then we need to reverse the order. And then finally, we have to calculate the future value of our savings plan after year 6. And now let's go on to the ABC company. And the company considers to buy a new machine for $2,000. And it expects a future profit or cash flow increase by the following amounts. And here we shall calculate the net present value. And based on the net present value and a required rate of return of 8%, we shall evaluate whether ABC should pursue the project. And last but not least, the final question, would ABC accept the project with a required rate of return of 10%? So that's coding exercise 2. And if you want to do it on your own, then please stop the video now. All right, now let's go to the solutions. And first of all, we can create a list with square brackets. And we pass the single elements or single cash flows separated by commas. And then we save the list in the variable CF. Then here we have to index the list for the following elements, today's saving. So that's the very first element at index position 0. So we have 0-based indexing. Then next we shall index for the saving in year 3. So that's the fourth element at index position 3. Then we have the second element at index position 1. And finally we have the final year saving. So the very last element at index position -1. So here we apply negative indexing. Next, we shall iterate over the list and print each and every element, and we can do this with a for loop. And we use here the for loop variable element, but we can use here any variable, so for instance I or whatever. And then we make a colon here and press enter, and then we get automatically an indent here, and then we use the print function to print each and every element. Here in question 4, we have to sum up all savings and all cash flows. And we can do this with a for loop, and we shall also print intermediate results. So first of all, we initiate here a variable total, and the initial value is 0. And then we iterate over CF, and for each and every element, we increment total by the element. And inside the for loop, we also print the intermediate results. And finally, we again print the very last, the final result. And we get here 14,700. So here we calculated the sum with a for loop, but there's also a Python built-in function, and it's the sum function. And within the parentheses, we pass the list CF. And of course, we get the very same result. And with the length function, we can determine the number of elements in the list. So we pass CF to the length function, and we have 7 elements. And actually, we not only can iterate over a list, but also over a range object. So we can say for I in range 101, and this is actually exclusive. So this is actually the range from 0 till 100 inclusive. And we print each and every element, so from 0 till 100. Then we shall create and save the list n with all timestamps. So in total we have 7 cache flows, starting at timestamp 0 till timestamp 6. And we use the range function here, so we pass 7 exclusive and actually transform the range object into a list with the list function. And we save the list in the variable n. So this is n. And next we shall reverse the order of n and reassign n. So we can actually reverse the order with the following code, :-1, and we reassign it to n. Now having the cash flow list and the list n with the reversed order, we can calculate the future value of our savings account after 6 years. And we can assume an interest rate of 4%. So we have 4% interest rate and therefore a compounding factor f of 1.04. And then we initiate a for loop and we start with the variable future value, which is 0. And then we iterate over each and every element in the list CF and increment the future value by the future value of each and every element. So we have here the respective cash flow times f to the power of the respective time period. And finally we print the future value and we get here 16,053. So now let's come to a simple capital budgeting problem. And actually ABC evaluates to buy a machine for 2,000 and it expects the following positive profits and cash flows. And ABC's required rate of return is 8%. And based on this, we shall calculate the net present value. So first of all, we create the cash flow list with the initial outflow and the inflows. And then we have the return of 8% and the discounting factor. And then we initiate the variable NPV and the initial value is 0. And then for each and every cash flow in the cash flow list, we calculate the present value and we add the present values. And finally, we have the sum of the present values of the positive inflows minus the initial outflow or plus the initial outflow, which is negative. So we iterate here over the cash flow list. And we end up with an NPV of 71. And this is greater than 0. And this means that we should accept the project. Finally, we shall do the very same calculation, but instead of having a required rate of return of 8%, we shall do this with 10%. So we have the same cash flows, but actually R differs. And this is the very same code, but with a different rate of return. And here we get a negative net present value, minus 61. And this means that in this case, ABC should reject the project. All right, this was coding exercise 2, and hope to see you also in the next exercise. Bye. In this course, we already got in touch with several data types that exist in Python, maybe without knowing it. So in this video, I will cover some of the most commonly used Python data types. And actually in Python, everything is an object. So we've already seen that we can save an object in memory and that we can assign an object to a variable. So here, for example, we have the number or the integer 100. This is an object in Python. And with the built-in function type, we can also check the data type. So here we have 100 and the data type is integer. So 100 is simply a number without any decimals. And we've already learned that we can divide the two numbers and assign the result to a variable. So here we can calculate the present value of the cash flow 100 and the interest rate is 3%. So here we have the object 97.08 and many more decimals stored in the variable PV. And again, we can check with the type function the data type of the object that the variable PV is referencing to. And it's a float, So here we have a number with many decimals, and this is actually a float object. And also the discounting factor of 1.03 is a float object. And even the object 1 point is a float, because when we type 1 point, then automatically we get the float and not the integer 1. So we have 1.0. Now lists are also objects, and they have the data type list. So what a surprise here. So here we have the type list. And also we have already worked with a range object. So we can assign to the range object from 0 till 10 exclusive. We can assign this range object to the variable n. And we can check the data type of n. And it's a range object. And also we have already used the built-in function print, where we can actually print numbers or lists. So for example, we can print out explicitly here the list CF. And also a built-in function is an object in Python and has a data type. So we can check the data type of the print function. And it is a built-in function or method. And again in Python, the general rule is that we can store objects in memory, and that we can assign objects to a variable. So we can also assign here the function print to the variable a. And then we can actually call the function, so we can print out the CF by passing here our list CF within the parenthesis here of a. So a is referencing to the function print. So this also works here. Next, we have the very important data type strings. And actually strings are simply a sequence of letters and also numbers, and can be used for names. So for example, Alex or Microsoft. And we can actually create a string by passing the sequence of letters here within quotation marks. So here we have Microsoft. And here we can see that this is a string, and we can see this here with the quotation marks. And also here we can check the data type with the type function, and we get str for string. And it's no surprise that we can also store strings in memory and assign them to a variable. So for example, here we have the variable company name, and we have Microsoft here. So the variable company name is referencing to the object Microsoft, a string object. Then next we have booleans, so true and false. And we can already see here in green that these are actually special keywords. So we have true, and we can check the data type of true, and it's a bool. And also false, this is also a boolean value. So these were very few examples of data types in Python. And the question is now, so what is a data type? And actually the data type of an object actually determines the functionality. So actually we can divide two numbers. So here an integer divided by a float. And we get here a result. And this only works actually because some developers defined that we can divide an integer by a float object. And if we try to do the same with a string, so we divide a string by 1.03, then we get here an error message, so unsupported operand type for string and float, so the divide does not work here. And also here this behavior and the fact that we get here an error message, a type error, is the result of the extensive work performed by the Python developers. And they actually defined the functionality of data types. And they did this actually in classes. So we could say that the string Microsoft is an object with the data type string, but we can also say that Microsoft is an instance of the class string. And we can also say that 100 has the data type integer, or is an instance of the class integer. And within these classes, the Python developers actually defined the functionality. Alright, this was a very high-level overview on object-oriented programming. Thanks for watching, and I'll see you also in the next video. Bye. This is an overview and the hierarchy of the most commonly used data types in Python. So we've already learned that in Python everything is an object, and each object has a data type. So for example, we have integers, we have floats, which are numbers. Then we have lists, we have functions like the print function, and also we have strings and booleans, true and false, and many more data types. And actually for each object, we can determine the data type, or alternatively, we could also say that each object is an instance of a class. And actually in classes, the functionality and the properties of data types are defined. And finally, each object has a memory address, so we can store each object in memory. So for example, we can store integers, floats, booleans, and also strings. So let's have a look at the hierarchy of some data types. And first of all, we have numbers, and there we have integers and floats, and also booleans. True and false are numbers, so we will see this later in the course. Then next we have collections, where we can store multiple elements or objects. And first of all, we have sequences. And here we can differentiate between mutable and immutable sequences. So mutable sequences like lists can be changed in memory. And in contrast to that, immutable sequences cannot be changed. So for example, tuples and strings. So later in the course, we will have special lectures on mutability. Then next we have sets, and also here we have mutable and immutable sets. And finally we have mappings like dictionaries. So these are the most commonly used collections provided by the Python standard library. However, and to be honest, there are more powerful data handling tools that are provided by special data science libraries like NumPy arrays, pandas data frames, and panda series. So later in this course, we will cover all these tools in detail. And finally, we have also callables. So for example, built-in functions like the print function or the length function are callables. So we can call these functions, and for example, we can pass a list within the parentheses of the print function and print out the list. Or with the length function, we can actually determine the number of elements in a list by calling the length function, and actually by passing a list within the parentheses of the length function. Then next we have built-in methods, and these actually work in the very same way as functions, but methods are actually specific for each and every data type and class. So there are different methods for integers and for strings. And finally, we can also define our own user-defined functions. So in many cases, we do not have to reinvent the wheel, and there already exists some built-in functions or methods. But sometimes we have to define our own user-defined functions, so that's actually real fun. Thanks for watching, and I'll see you also in the next video. Bye! This is an excursus to dynamic typing. So dynamic typing is the opposite of static typing, and if you are familiar with other programming languages, you might be used to static typing. And in this regard, Python works here different. So here we have dynamic typing. And let's have a look on dynamic typing. So we can assign the integer 100 to the variable a. And then we can check the data type a. It's an integer. So actually the variable a is referencing to the integer object 100. Then next in Python we can change the reference of a variable. And we can, for example, assign the string object Facebook to the variable a. And now we can check the data type of the object that the variable a is referencing to, and it's now a string. And finally, we can also assign a list to our variable a, so that's no problem. And a is now referencing to the list. So no problems here. This works perfectly in Python because we have dynamic typing in Python. However, in other programming languages, this does not work. So once we have assigned the integer 100 to the variable a, then the variable a has been declared as an integer and cannot be assigned the string value Facebook later on. So here in Java, we would actually get an error message. Alright, thanks for watching, and I'll see you also in the next video. Bye. In this lecture, we will go through some of the most commonly used Python built-in functions. So built-in functions have been created to perform some of the most frequently used workflows in an easy and efficient manner. So for instance, if we want to determine the number of elements in a list, we can do this with a for loop, but this is pretty inconvenient and Python coders have to reinvent the wheel again and again. So to avoid this, there are some helpful built-in functions like the length function. Alright, let's assume that we save $100 for 1 year at an interest rate of 3%. Then, of course, we can assign to these input factors some variables, and we can calculate the future value. And we've already worked with the built-in function print. So here we can actually display values in the output. So for example, we can print the future value. And it's here 103. And actually built-in functions have one thing in common. So typically they can be performed on different data types. Or to put it the other way around, we can pass different data types to built-in functions. So for example, here we passed a float object to the print function, but we can of course also print here a string, Facebook, or we can also print a list. And actually most functions give some flexibility and options to customize things. So for example, the print function allows to print many objects. So here we have many objects separated by a comma. And functions typically also have parameters like the separator parameter. And here in this example, we can define how the values that we print out are separated in the output. So for example, here we can pass the argument a new line to the separator parameter. And let's have a look here. So here we have the present value, the interest rate, the number of periods, and the future value in the separated lines, but we can also pass another argument to the separator parameter, so for example, comma, and by doing so, we separate the output values only by commas. So here we have the output separated by commas. Alright, next let's create the list cache flows with in total 6 cache flows. And then we have already learned that with the length function, we can determine the number of elements in the list. And alternatively, we can also do this with a for loop, but no need to reinvent the wheel here actually. So we have 6 elements, and actually to the length function, we can pass all kind of sequences. So a list is a sequence containing different values, but also a string is a sequence containing many letters. So for example, Facebook has in total 8 letters here, and therefore we can also pass here the string Facebook to the length function, and here we get the result 8. And finally we can also try to pass an integer to the length function. And here we get the error message that the object of type integer has no length function or no length. And actually these behaviors here have been defined in the classes. So for example, in the integer class, it has been defined that there is no length for an integer, for example. Alright, now let's go to the sum function. And also here we can pass a sequence like our cache flow list. And here we get the sum over all elements, 90. And we can also try to pass the string Facebook to the sum function. But here we get an error message, so unsupported operand type plus for integer and string. Next, we can also get the minimum value in the cache flow list with the min method. And we get minus 200. And then we can also try to apply the min function on a string, so for example, Facebook. And we would actually expect to get the minimum alphabetical value, and here it's an A. So let's try this out. And here we get capital F, so this is an unexpected behavior actually. And for the min function, capital letters come first. And here we only have one capital letter, so F, and therefore we get here F. And let's try to do the same with a lowercase f here. And then we get A. So we should be careful when we use built-in methods and functions, and we should try to understand what is going on in the background. Otherwise, we will be surprised by some strange behaviors here. And with the max function, we can also get the highest or the maximum element. And in case of our cash flow list, it's 100. And for Facebook, so here we would expect actually an O here. And this is true. All right, these were a few Python built-in functions, but there are many more. And let's have a look. Here we have all available Python built-in functions. So for example, we have the range function or the print function and the length function. And later on in this course, we will examine many other functions. But for the time being, we have reached the end of this video, and I hope to see you also in the next one. Bye. We have already seen the integer data type. And actually, integers are whole numbers without decimals or fractions. So for instance, 100 is an integer, and we can check this with the type function. And of course, we can perform arithmetics with integers. So for example, addition, subtraction, multiplication, and division. And if we divide two integers, then we get actually a float object, even if the result itself is also an integer. So 10 could be an integer here. But as we can see here, we have 10.0, and this is a float. So let's check this. Before we have learned that in Python we can store objects in memory and assign objects to variables. And of course also integers are objects, and we can store them here, for example, in the variable I0. So the investment at the timestamp 0. And actually we could also say that the integer 100 is an instance of the class integer. And actually integers have some built-in methods. So built-in methods are actually very similar to built-in functions, but methods are actually specifically designed for a class or data type. So an integer object, for instance, has different methods than, for example, a list. And there are very few methods for integers. And actually one method is the bit length method. And we can actually call a method by having here the variable that is pointing or referencing to the object. And then we have a dot. And then we have to code the method. So here in this example, it's bit length. And same as with the built-in functions, we need some parentheses to call the function or the method. And actually there are many methods where we can pass arguments here inside the parentheses, but not here with the bit length method. So now let's simply run the cell, and we get here 7. And we can also go here inside the parentheses and press Shift tab. So we hold Shift and press tab. And by doing so, we get here some information on the method. So for example, the description or docstring that the bit length method returns the number of bits necessary to represent the integer in binary. So we are using here a computer, and typically we are working with decimal numbers and the decimal system. However, in our computer, the decimal numbers have a binary representation, so the binary system. And the bit length method actually returns the number of bits necessary to represent the integer in binary. And in this case here with 100, it's 7 bits. Alright, thanks for watching, and I'll see you also in the next video. Bye. Alright, we are coming now to floats, and floats are actually numbers with decimals. For instance, 1.04, we have here 2 decimals, and we can also check the data type. And it's no surprise that this is a float. And in case we divide one integer by another integer, and even if we get here another integer, so here 10, then this is actually a float here then in Python, so after division. So 10.0, and we can also check the data type, it's a float. And we've already learned that in Python we can store objects in memory and assign to a variable. And of course, we can also do this with float objects. So we can save the object 1.04 and assign it to the variable r. And then, for instance, you can perform some arithmetics, multiplication. 100 times 1.04 gives 104. And actually, there are also some built-in methods for floats. So let's have a look here with the tab key. So we have the sinteger ratio method or the isinteger method. So let's have a look here inside the parenthesis with shift tab. And the isinteger method actually returns true if the float is an integer. And with 1.04, we should get actually a false. And that's true. And let's also have a look at the method sinteger ratio. And this method actually returns the integer ratio. So each and every float is actually stored as an integer ratio, a ratio of two integers. And let's have a look how 1.04 is internally stored or represented. So actually 1.04 is the ratio of this large integer and this large integer. Next, let's come to some strange behavior and obviously some bugs in our code. But this is actually not a bug, and this is also not Python specific. And now let's make the following calculation. So we add 0.1 3 times, and then we check whether this is equal to 0.3. And actually it should be equal, but we get here a false. And this seems to be a bug, but this is not a bug. And to understand this behavior here, we have to understand how floats are actually internally represented. And first of all, let's have a look at 0.1. So we get here 0.1, but if we add here 0.1 3 times, then we get the result of 0.3. And then in the 15th decimal, we get a 4. So this is not exactly 0.3. And it seems like that 0.3 is exactly 0.3. But let's check this in more detail, and we can do this with the built-in function format. And here we can pass the float, so for instance 0.1 or 0.3, and then we can define how many decimals the format function shall display. So this means here 20 decimals, and let's have a look at 20 decimals of 0.1. And here we get 0.1, and then finally in the very last 3 decimals we have 555. So 0.1 is not exactly 0.1, and let's check this also for 0.3. And also 0.3 is not exactly 0.3, so here we have 0.299 and finally here 8890. And actually this behavior is not Python specific, so we're working here on a computer with a binary system, so 0 and 1. And numbers in a computer are represented using bits and not decimal digits. So all numbers have a binary representation, 0 and 1. And therefore some decimal numbers with finite representation, so 0.1 and 0.3 have a finite representation in the decimal system, but they do not have a finite binary representation, so that's simply impossible. So let's have a look at a float example that has a finite binary representation, for instance 1 divided by 8, so 8 is 2 to the power of 3, and this should work in the binary system, so we have here 0.125, and let's also get 20 decimals. And 0.125 is actually the exact representation. And as another example, 1 divided by 32 has also a finite binary representation. So 32 is actually 2 to the power of 5. And let's check this here. And 0.03125 is the exact representation also in the decimal system. So the question is now, can we get a more precise representation for 0.1? So for instance, by rounding, but this is simply impossible because still we are here in a computer with a binary system. So we can try to round 0.1 to 1 decimal, but if we check this with the format function, then we can see here that even with rounding, we cannot make 0.1 more precise here. Alright, thanks for watching, and I'll see you also in the next video. Bye. We have already used the Python built-in function round in the last lecture, and in this lecture we will examine some more options how to round the floats and also integers. So let's start with the float 1.3454, and actually we can round this to the next integer. So let's have a look here inside with Shift tab, and actually the round function rounds a number to a given precision in decimal digits. So we have two parameters here, the number parameter, where we have to pass the number, and we have the n digits parameter. And here we can define the precision or the number of digits, and the default behavior is that actually we get the very next integer. So let's run the cell here, and here we get the next integer, which is 1. So we round the 1.3454 down to 1. And now let's have a look at the number 1.7657. So if we apply the round function here, then by default we round the number to the next integer, and in this case it's 2. And we've already seen that we can define a precision and a number of digits. So for instance, we can also round to a 1 digit, 1.34. Let's have a look here, and here we get 1.3. And we can also pass 2 decimals. And here we should actually round up to 1.35. Let's have a look here. And this is true. And we've already seen that there are numbers that cannot be represented with a finite binary representation. And also rounding does not help us here. So again, we have the case where we want to round 1.3454 to 2 decimals. And then we check the first 20 decimals with the format method. And also here we can see that with the rounding we do not get exactly 1.35. So we have 1.35, and in the 18th and 19th decimal we have some 8s here. Alright, now let's go on. And we not only can round floats, but we can also round integers, for example, to the next multiple of 10 by passing here minus. So by passing here -1, we round to the next multiple of 10. And in this case, we should round down to 10. And having 17, we should round up to 20. And of course, we can also round to the next multiple of 100 by passing -2. And having here 217, we should round down to the next multiple of 100. And this is here 200. And 257 should give 300. So 300 is the next multiple of 100 for 257. And now let's come to kind of a strange behavior. So let's try to round 1.5. And this is actually a tie, as the distance to the next multiples is equal. So we have 0.5 distance to 1 and a distance of 0.5 to 2. And let's check this here. And here we get 2. And now let's try to round 2.5. And also here we would expect that we round up to 3. But this is obviously not the case. So also here we get 2. And this behavior is actually the so-called banker's rounding. And it actually seems arbitrary, but there's a real benefit of banker's rounding. So let's assume that you want to add 1.5, 2.5, 3.5, and 4.5. And this gives 12. And now let's assume that 0.5 is always rounded to the next lower integer. Then we should receive the following result, which is clearly pretty far away from 12. So we have here 10. And now let's check what we really get when we use here the round function on each and every element. So do we get 10 or 12? And we actually get 12. And again, this is the so-called banker's rounding. And it works in a way that the ties are rounded to the nearest or next value with an even least significant digit. So in our example here, we round to the next even integer. And in case of 1.5, it's 2. In case of 2.5, it's also 2, so 2 is an even number here. And we can see that bankers rounding leads to less biased rounding. So if ties are always rounded to the next higher or to the next lower integer, then we get here actually very unprecise results. So on average, 50% of all ties will be rounded up and 50% will be rounded down. Alright, thanks for watching, and I'll see you also in the next video. Bye. In this lecture, we will examine lists in more detail. So lists are collections and more specific sequences where we can store many objects. So for example, here we have our cash flows, 6 in total, and we create a list and assign it to the variable CF. Then next we can check with the built-in function type, the type, so this is a list. And we can also determine the number of elements in our list with the length function. So in total we have 6 elements. Then with the built-in function sum, we can calculate the sum over all elements. And here we have 90. Then next we have the built-in function max. And here we can determine the maximum element in our list, CF. And it actually should be 100. So let's have a look here. And we can also determine the minimum element with the min function. And we've already learned how to index a list or a sequence, and the so-called zero-based indexing applies. So if we want to get the very first element, so here minus 200, then this element is at index position 0. And we can actually index lists here with a square bracket. And there's also the concept of negative indexing. So for example, if we want to get the second last element, then we can pass here minus 2 and we should get the element 100. Lists have also some built-in methods, and let's have a look here. So we have CF dot, and let's press the tab key to get a drop-down menu. So here we have the built-in methods for lists. So for example, we have the append method, the copy method, and also the index method. And we also need here some parentheses. And actually, in the index method, we can actually pass a value, and we can check the index position of the first occurrence of this value. So for example, in our list, we have the value 70, and the very first occurrence we have at index position 3. So if we pass here 70, then we get the index position 3. And we can also try to pass a value that is not in our list. So for example, 59. And here we get value error. So 59 is not in our list cash flows. Next, there's the Python built-in function enumerate. And here we can pass our cash flow list. And by doing so, we create a enumerate object. And we can actually unpack an enumerate object with the list function. So we pass the enumerate object here within the parentheses of the list function. And here we get a list, and the list actually contains tuples. So we can see here with the parentheses, so these are tuples containing 2 elements. And later on in this course, we will have a closer look on tuples, but for the time being, so here we have index value pairs. So we have the value minus 200, and this is at index position 0. Then we have the value 20, which is at index position 1, and so on. Next, we have the built-in method count, and count actually returns the number of occurrences of one value. So for example, here we have one time the value 20, and by passing 20, we should get the number of occurrences. So in this example, it's 1 occurrence. And finally, it's pretty important to understand that in a list, we can store different objects of different data types. So for example, we can store integers and also floats. For example, 50.2, and we can store strings and Boolean values. So this is no problem here. And we can also iterate over the list and determine for each and every element in our list the data type. So let's do this here. And here we can see that we have 4 different data types in our list. We have integers, floats, strings, and booleans. And this is actually an important characteristic of lists, that we can store objects of different data types here. And this also determines the functionality of lists and also the performance of lists, for instance, in element-wise operations. So later in this course, we will see that, for example, in a NumPy array, it's only allowed to have 1 data type. And actually, in the end, that's the reason why lists and NumPy arrays behave differently. But we will see this later in the course. But for the time being, we are now finished, and I hope to see you also in the next video. Bye. In the last lecture, we have learned that we can store objects of different data types in lists. However, this flexibility comes at a cost. So it limits element-wise operations with lists. What do I mean with element-wise operations? So let's assume that we have forecasted future cash flows for an investment project. So for example, 100 in 1 year, 10 in 2 years, and so on. So let's create the list here. And then we get some positive news that allows us to update our forecasts. Say we now expect 10% higher cash flows. Then it would be great to simply multiply each and every element in our list with 1.1. So let's try this out. And we get here an error message. So this is not how lists work. Let's have another example, and let's assume that we need to update our forecast, as there is an additional fixed cost of 20 per year. Then consequently, we need to subtract 20 from each and every cash flow in our list. And let's try this out here. But again, this is not how lists work. So there's a workaround with a for loop. But first of all, let me introduce the append method. So we can create a list with the elements 1, 2, and 3. And with the append method, we can actually add another element at the end of the list. So for example, here the element 4. And here we have actually 4 at the end of our list here on the right-hand side. And also we can create empty lists. So we have here square brackets with no elements. And we can assign the variable cash flows new. So this is possible here. All right, now we are equipped to perform element-wise operations. And actually we want to create a list with cash flows increased by 10%. And therefore, first of all, we create the empty list cash flow new. And then we iterate over the list cash flows. And for each and every cash flow, we actually multiply the cash flow with 1.1 and store the increased cash flow in the variable new. And then we append the increased cash flow, which is stored in the variable new, to our new list. And this we will do for all loops or for all cash flows. And finally, we print our cash flow new list. And here we have our cash flows, all our cash flows increased by 10%. And the same we can do also for our second example. So we can subtract 20 from each and every element in our list cash flow. And again, we create the new list, the cash flow new. It's an empty list here. And we iterate over each and every element in our cash flow list. And we actually subtract 20 from each and every element. And then we append the new value to the new list, the cash flow new. And finally, we print out the new list here. And here we have all values reduced by 20. And finally, there's actually one last thing that I want to show you. So before we have seen that we cannot multiply a list with a float object. So our cash flow list multiplied with 1.1 does not work. However, we can actually multiply a list with an integer. So for example, 3. So let's have a look here. And actually, instead of multiplying each and every element with 3, we created here 3 copies of the list and actually concatenated the 3 copies into one list. So we have 3 times the sequence 100, 10, 20, 50, 30, and 25. So if our intention was to multiply each and every element with 3, then actually this result is pretty surprising actually. Alright, thanks for watching, and I'll see you also in the next video. Bye. We have already learned how to get or access single elements in a list. This is called indexing. However, we can also slice a list. That means that we can get or access many elements or subsets of a list. And actually the very important concepts of zero-based indexing and negative indexing apply also to list slicing. So let's assume that here we have our list with 6 cash flows. And now we want to get or we want to slice for the elements 20, 50, and 70. So here we have the index positions 0, 1, 2, and 3. And we can actually slice for this subset by opening square brackets here. And then we can slice from the second element at index position 1 inclusive. So here it's 20 until, so colon stands for until the element at index position 4, it's 100 exclusive. So let's run the cell here. And here we have the subset 20, 50, and 70. So let's have another example. And let's slice from index position 0 inclusive until index position 1 exclusive. And here we only get the very first element minus 200. And actually when we slice from the very first element, we can also have the following notation. So colon 2 means that we slice from the very first element until the third element at index position 2 exclusive. So here we have minus 220, so the first two elements. And we can also slice from a specific element until the very last element inclusive. So for example, let's assume that we want to get all elements from the second till the last. Then we have here 1 colon. And here we have all elements except the very first element, minus 200. And finally, we can also slice for all elements by simply having here colon. So from the very first till the very last inclusive. And as I said before, also negative indexing applies to slicing. So for example, we can get all elements except the very last element. So from the very first element until the very last element exclusive. So here we have all elements except the very last one, 50. Next we can also get the last 3 elements. So we slice from the element at index position minus 3 inclusive until the very last element inclusive. And here we have 70, 100, and 50, so the last 3 ones. And finally, we can also get every second element. So the first colon here stands for all elements, so all elements from the beginning till the end. And then we have an additional colon 2, and this means that we only get every second element starting from the very first one. So let's have a look here. So we get minus 200, 50, and 100. So minus 200, then the second next 50, then the second next 100. Next we can also slice from the second element at index position 1 until the 6th element exclusive, but only every second element. So this is also possible. And finally we can also select every third element here. And last but not least, we can also reverse the order. So we actually slice our list and select all elements, so from the first one till the last one, and then every minus 1 element, and that means that we actually reverse the order here. So here we get 50, 100, 70, 50, 20, and minus 200. Alright, thanks for watching, and I'll see you also in the next video. Bye. Changing or modifying elements in a list is a typical workflow. So let's create the list CF with our savings plan. So we save 100 today, 10 in 1 year, and so on. However, plans can change, so we decide to deposit today only $50 instead of $100. And actually lists are mutable objects. And that means that we can change or modify elements in a list. So later in this course, we will dive deeper into mutability of objects in Python. So that's a pretty important topic. But for the time being, it's sufficient to understand that we can modify elements in a list. And this is actually pretty straightforward. So we have to index for the element that we want to change. So in this example, it's the very first element at index position 0. So here we would index for 100. And then we can assign the new value 50. So let's run here the cell and let's check again our list CF. And here we have successfully changed the very first element to 50. And actually we can also change or modify many elements in a list. So let's assume that we want to have ongoing and constant savings of $40 per year. Then we can simply slice for the elements that we want to modify. So here all elements starting from the second element. And then we can try to assign the new value 40. And here we get an error message, can only assign an iterable. And what we tried here is so-called broadcasting. So we tried to broadcast a scalar value, so 40, to more than one element here in our list. And broadcasting actually does not work with lists. However, we can assign a list with our desired new values. So here we have a list containing 5 times 40. And then we can actually slice for the elements that we want to change and assign here the new values. So let's try this out. And this works. So today we save 50 and in the next 5 years 40. And of course we can also have different values here. So for example, we could save in 2 years 70 and in 5 years maybe only 10. So this also works. Alright, thanks for watching and I'll see you also in the next video. Bye. In this video I will show you how to sort lists and how to reverse the order or the sequence of a list. And you might recall that we have already reversed the order of a list when we calculated net present values. So we created the list n with integers from 0 till 5. And then we can reverse the order with the following slicing, so :-1. So here we have the sequence 5 till 0. However, it's important to understand here that we didn't change the original list n. So we simply created here a new object with a reversed order, but the variable n is still referencing to the original list from 0 till 5. So let's check this. So this is still our original list. And if we want to change the referencing of the variable n, then we have to reassign n to the new object. So with this code here. And now n is actually referencing to a new object with the reversed order. However, there's also a second option how to reverse the order of a list. And we can actually do this with the built-in method reverse. So we simply use the method here on our list n. And let's check n here. And apparently the reverse method reversed and changed the list in memory in place. So here in this example, we did not create a new object, but we changed actually our original list n. And this is also called changing an object in place. Now let's create a new list with some cash flows, so 110, 20 and so on. And we assign it to the variable CF. And there's actually the sort method. And the sort method actually sorts the elements in the list from low to high. So let's run the cell here and let's check CF. And here we can see actually the sorted list from low to high, so from 10 till 100. And also here we have changed our object, so the list here in place. So we modified the list and we actually did not create a new object or a copy. Last but not least, there's also the option to sort the elements in the list in reverse order, so from high to low. And we can do this by passing true to the reverse parameter. So the default argument is actually false. So by default, we sort our list from low to high. But we can also pass true here. So let's try this out. And here we get the reversed order from high to low. And for the sake of completeness, we can also pass false here to the reverse parameter. So let's try this out here. And by doing so, we should actually sort our list again from low to high. And this is true. And as I said, this is the default behavior of the sort method. So sorting the list from low to high. And if you want to have the default behavior, then we do not explicitly pass here false to the reverse parameter. Alright, thanks for watching, and I'll see you also in the next video. Bye. In this video, I will show you how to add and remove elements from or to a list. And again, here we have the projected cash flows for the XYZ company's investment project, buying an additional machine, starting with the initial outflow or investment of 200. And now let's assume that the machine can run for another year, year 6, and produces in this year additional profits or cash flows of 25. So we should actually add the element 25 at the end of our list. And let's try to do this with cash flow plus 25. And we get an error message here, and it says can only concatenate list to list and not to an integer. And that means that we can merge or concatenate a list with a list. So we have to put the additional cash flow of 25 into a list. And then we can add the two lists and actually merge them. So let's have a look here. So here we have our new and updated list with 25 here at the very end. However, it's important to understand here that we didn't change our original list. So here we created a new object with the additional 25 at the end. And the variable cf is still referencing or pointing to our original object here. So let's clarify this here. So still we have here our original list without the 25. And if you want to add to the 25, then actually we have to reassign here the variable to the new object that includes 25. Alright, now let's assume that our machine can run for an additional year, year 7. And here we project additional cash flows of 10. And there's actually a second option how to add elements to a list. And we can do this with the append method. So we have already seen the append method. And actually the append method adds an element at the end of an existing list. So here the CF list. And at this point, actually, I want to introduce a very helpful tool. So it's called the tooltip. And we can go here inside the parenthesis of a method or a function. And then we can press Shift tab. So we hold Shift and press the tab key. And by doing so, we can get here some more additional information and explanations on the built-in method or built-in function. So here we can see the append method, and within the parenthesis, we can pass an object that we want to add to the list cash flow. And it says here that the append method appends objects to the end of the list. And actually it's a built-in function or method. So this is pretty helpful. And let's run the cell here. And actually the append method changes or modifies our original object. So here we do not create a new object, but we change our original list that is assigned to the variable CF. So let's have a look at CF. And here we can see that now we have 10 here at the very end. So again, it's important to understand that with this code, we are actually creating a new object, and we have to reassign the variable here to the new object. And with the append method here, we actually change or modify our existing object, so the list here. So that's a difference. All right, now let's assume that we can use the machine for another 2 years with additional cash flows or profits of 5 and 2. So we want to add here 2 elements to our list. And again, we can do this here by concatenating or merging 2 lists with a plus sign. So this works pretty good. But also here it's important to understand that here we are creating a new object. So we do not manipulate or change our original object that is assigned to the variable CF. So CF is still here referencing to our original list without 5 and 2 here. And again, we have 2 options here. So the first option is to reassign the variable CF to the new object, or we use the extend method and actually modify and change our existing list or object. So here, let's have a look inside the parentheses with the Shift tab. And here we can see that the extend method extends a list by appending elements from the iterable. So here we have to pass inside the parentheses an iterable, so for example a list with 5 and 2. And by doing so, we are extending the list CF by these 2 elements. So let's run the cell. And we are actually changing our original object, our original list. So now we have CF and we have 5 and 2 here at the very end. Next, we decided that it is not worth to run the machine for the very last year, where we only get 2 as cash flow or profit. And then we decide actually to remove here the very last year. And we can do this here with the remove method. So let's have a look here with Shift tab. And it says the remove method removes the first occurrence of a value. So if we pass here 2, then it's important to understand that we only remove the very first occurrence. So for example, if we had 2 also here, then only the 2 here is removed and not the 2 at the end of our list. But as we only have the element or the value 2 once here on our list, then with the remove method, we should actually remove here this element here. So let's have a look. And this is true. And also here it's important to understand that the remove method actually changes or modifies our original or existing object. So we do not create here a new object. So we manipulate here the object that is assigned to the variable CF. And now finally, let's assume that we want to go back to our original list. So until 50, and that we want to delete 25, 10, and 5. Then this does not work with the following code. So we cannot deduct a list from a list. And actually, if we want to delete the last 3 elements in a list, then it might be best to slice our list here. So for all elements except the last 3 elements, and then we reassign the new object that we create here to the variable CF. So now again we have our original list. The pop method is another method that I want to show you here. So let's go here inside the parentheses. So the pop method removes and returns item at an index. And the default argument for the index parameter is -1. So by default, if we use here the pop method, then we remove the very last element at index position -1 from the list. And at the same time, we return the element. So let's simply have a look here. So the pop method actually returns here the very last element. And at the same time, it actually removes the last element from the list. So now let's have a look at the list CF. And here we can see that the very last element, 50, has been removed. Finally, there's the insert method. And let's have a look here inside the parentheses. And it says here the insert method inserts an object before an index position. So here we have 2 parameters. So we have the index parameter and the object parameter. So let's have a look at the first argument here for the index parameter. So here we can define at or before which index position in our list we want to insert the object, which is here at the second position. So here we want to insert 100 before the element at index position 2. So we have here index position 0, 1, and 2. And actually here we would insert the new element 100. So let's have a look here. And let's check CF. And here we have now the element 100 inserted. And also here we have the case that the insert method actually modifies or changes our original list. So we do not create a new object, but we change the existing object in memory. Alright, thanks for watching, and I'll see you also in the next video. Bye. We are coming now to one of the most important concepts in Python, mutability of objects. And if you want to avoid the most frequently made mistakes in Python, then you should follow the next 2 lectures carefully. We have already seen the following example. So we have an interest rate of 5% and we assign it the object here to the variable r1. And now let's assume that we create a second variable r2 and we want to have the same value here, so 5%. So r2 is also 5%. And then we increment r1 by 1 percentage point. And if you think now that r1 and r2 are 6%, then you are wrong. So r1 is actually 6%, but r2 is still 5%. So let's have a detailed look what is going on here in memory. So that's our memory with some slots and their addresses. And we code r1 equals 5%. And by doing so, we create a new object, 5%. At the slot with the memory address 0x1000, and we create actually the variable r1, which is pointing or referencing to the object here. Then next we have the code r2 equals r1, and by doing so we create the variable r2, and actually r2 is pointing or referencing to the very same object as the variable r1. Next, we are incrementing r1 by 1 percentage point, and what we actually do here, we do not change or modify the object that r1 is pointing to, so we do not change here the 5%, but we create a new object, 6%, and we are actually changing the reference of the variable r1. So we delete here the reference to the object 5%, and we create a new reference to the object 6%. However, the variable r2 is still pointing or referencing to the object 5%. And that's the reason why we didn't change r2. So we incremented r1, but we didn't change r2. And actually the reason for this is that integers and also float objects are immutable objects. So once we have the object here in memory, so we cannot change the object. We can create a new object. So we can increment by 1 percentage point and create a new object, but we cannot change the object here. All right, now let's go to lists, which are actually mutable objects. So we create here the list with 6 cache flows, 100, 10, 20, and so on. And we assign it to the variable cf1. And then we also create a second variable, cf2, and we want to have the same list here for cf2. So we have the same values or the same list here for cf2. And now we want to change the very first element of cf1. So instead of having 100, we want to have 50. And if you think now that we did change cf1, but we didn't change cf2, then you are wrong. So we also changed the very first element of our variable cf2, or the list that cf2 is referencing or pointing to. So in both lists here we have 50 as the first element. And again, let's have a look what is going on here in detail in memory. So here we have a view on our memory, and we create a list object, so with 6 elements. And we create actually the variable CF1, which is pointing or referencing to the object. And then we create a second variable CF2, and actually CF2 should reference or point to the very same list. And then we change or modify the very first element in the list, CF1. And actually we do not create a new object here. So we change or we manipulate the existing list or the existing object. And let's have a look here. So we simply change the very first element on our list. So we have now 50 here. And here we have the situation now that not only CF1 has changed, but also CF2, or to be more correct, the object that CF2 is referencing to, because it's the same object that CF1 is referencing to. So as a summary here, we can say that lists are mutable objects, so we can change or manipulate lists in memory. All right, now let's go back to our Jupyter notebook. And let's have another example here. Again, we create here the list, and we assign it to the variable CF1, and we create CF2. And then we append another object here to CF1, 15, and we do this with the append method. And let's print out CF1 and CF2. And here we can see that we have changed CF1 and CF2. So that's the first alternative how we can append additional elements to a list. But there's also a second alternative which works differently in memory. So again, we create the list here and we say CF2 is CF1. And then we actually concatenate two lists, so CF1 and 15. And by doing so, we create here a new object and we reassign the variable CF1. And if we check now CF1 and CF2, then here in CF1 we have the additional element 15, but we do not have this here in CF2. So again, let's have a detailed look how this works in the background. And again, we create the object or the list with 6 elements, and we have the variable CF1. Then we create the second variable CF2. And then we append the element 15 to a CF1, and actually we change the existing list. So lists are mutable, and the append method actually changes existing lists, so CF1 for example. So here we have 15 at the very end of the list, and we can also see that of course CF2 is also referencing or pointing to the changed list or object. And we can also say that the append method changes or mutates the lists in place. And let's have a look at the second alternative. So here our list was modified or changed. And actually variable reassignment is a completely different concept. So again, we create here the object, the list, and CF1 is pointing or referencing to it. Then we create CF2. And then we have the following code. So we add the element 15 to CF1. But what we actually do here, we create a new object or a new list with 15. And we actually change the reference of CF1. So this is called variable reassignment. So we delete here the reference to the original list and create a new reference. And as a consequence, so CF2 is still referencing or pointing to our original list without the additional element. So the original list wasn't modified or changed here. All right. So now let's have one last example here. And again, we create the list CF1, and we say CF2 equals CF1. And we have already seen that with the sort method, we can sort a list in place. So let's do this here. So we sort CF1 in place. And of course, we have changed CF1, but we have also changed CF2. And the reason is that the sort method actually changed or mutated the original list. And actually both variables, so CF1 and CF2, are referencing or pointing to the same original list. Alright, thanks for watching, and I'll see you also in the second part. Bye. Welcome to the second part on object mutability. And we've already seen the following situation. So we create a list and assign it to a variable cf1. And we also create a second variable cf2. And both are referencing or pointing to the identical object. However, there are cases where you actually want to create a copy of an object or the list here, where cf1 and cf2 are referencing to different objects, so to copies. And if you change one object, so for example cf1, you do not change the other object where cf2 is referencing to. And there are actually 3 ways how to do this with lists, 2 bad ones and 1 good one. So let's have a look here. So this is the first alternative, and we can simply create the identical list 2 times and assign it to 2 different variables, cf1 and cf2. And when we change now the very first element of cf1 to 50, then we do not change actually cf2. So here still we have 2 different lists. So let's have a look what is going on in memory. And here we create the first list and assign it to the variable cf1. And then we create the identical list. So that's a different object, and we assign it to the variable cf2. And if we change now cf1, so we change the very first element to 50, then of course we do not change the object that cf2 is referencing to. So this solution works here, but it's pretty inconvenient to create the object here 2 times. So this is definitely not an advisable solution here. So let's have a look at the second solution. And again, here we create the list and assign it to variable cf1. And then we slice here cf1 and we select all elements in cf1 and assign all elements to cf2. So we assign the slice here to cf2. And actually when we slice lists, then we create a new object. So cf2 is actually referencing to a different object here. And let's modify or change cf1. So if we do this, then we do not change cf2 because cf2 is actually referencing to another object. And again, let's have a more detailed look here. So we are creating the object here and we have a variable cf1. Then we actually slice cf1, and by doing so we create a new object. So with the same elements, and we have the variable cf2. And again, if we change or modify cf1, then of course we do not change cf2 or the object that the cf2 is referencing to. So this solution works in case of having lists here, but for example, we will see later with NumPy arrays that it's not guaranteed that when we slice a list or a NumPy array, that we automatically create here a copy. So when slicing lists, we create actually a new object or a copy, but this is actually not guaranteed for other collections or sequences, like for example NumPy arrays. So this is also here not an advisable solution. And finally, now let's come to the best solution. And again, we create the list and assign it to the variable cf1. And then we can actually create a copy of cf1, so a new object with the copy method. So we create here a new object and we assign it to cf2. So cf2 has of course the same elements here. And if we change cf1, so the first element, then we actually do not change cf2. Again, let's have a more detailed look here how it works. So that's the best solution here. And again, we have cf1 and the list here. And then we create a copy of cf1 with the copy method. So we have here a new object with the same elements. And we assign it to the variable cf2. And of course, if we change cf1 now, then actually we do not change cf2. So if you want to work with two different objects and copies, then you should always use here the copy method. Alright, thanks for watching, and I'll see you also in the next lecture. Bye. Welcome to coding exercise 3. We are here on the Jupyter dashboard, and we have our course materials part 1 on our desktop. So course materials part 1, exercises, and now we are going to exercise 3. And actually exercise 3 covers integers, floats, lists, and built-in functions. And these are very essentials of Python coding. So first of all, here we have to create integers, floats, strings, and booleans of our choice. And we should explicitly check the data type. Then next here we have a list L, and we should use some built-in functions. So for instance, we shall calculate the sum and the number of elements and the maximum. And we shall do the same not only for a list, but also for a string. Next, we shall check whether the following calculation is true. And we shall examine why this is true or not true. And then we have to round a float to 2 decimals and check the first 20 decimals. Then next we can also round to a multiple of 10, 100, 1000 or whatever. Next we shall create slices of a list. So this is a very important topic here. And we should add elements to a list and also change elements in a list. And finally we also have to remove elements from a list. And then we have to perform element-wise operations, so adding 20 to each and every element. And we have to sort the values in a list from high to low. And finally, we have a very important topic, mutability of lists and objects. So this is coding exercise 3. And if you want to do the coding exercises on your own, then please stop the video now. Alright, now let's move on with the solution. In Python, everything is an object, and for instance also the integer 14 is an object that we can store in memory and that we can assign to a variable, for instance a. And then we can also check the data type of a, and it's no surprise it's an integer. Next we have the float object 12.56. And then we have the string Twitter within quotation marks here. And finally we have a boolean value, so we have true and false. Next we have the following list with in total 8 or 9 elements. And actually we shall use the built-in functions to calculate the sum. And here we can use the sum function and pass the list L to sum. So first of all we have to define the list and save the list. And now it works, minus 405. Then with the length function we can determine the number of elements. And in total we have 9 elements, and we can also determine the maximum element with the max function. And here we get 340. So here. And actually the key message is that we not only can pass integers or floats to built-in functions, but also other data types like strings. And here we have the string s, and don't ask me to pronounce it. So this is a real word, an existing word, but I don't pronounce it here. So let's save s, and we can determine the length of s, and it's 14. And we can also determine the alphabetically first value with the mint function. And here we get c, but this only works because we have only lowercase letters here. So if we had uppercase letters, then these come first actually. Now we have the following equation, 0.2 plus 0.2 plus 0.2 equals 0.6. And intuitively this should be true, but in Python this is false. And the reason is pretty simple, so we can check the first 20 decimals of 0.2 with the format function. And here we get the result 0.2, and then here in the last decimals we have 111. So 0.2 is not exactly 0.2, and also 0.6 is not exactly 0.6. And the simple reason for it is that we are here on a computer in a binary system, And there's actually no finite representation for 0.2 or 0.6 in the binary system. And therefore there's also no exact and finite representation in the decimal system for these numbers here. And actually rounding does not help us, so here we shall round 1.56456 to 2 decimals. And we can actually do this with the round function and pass the number and the amount of decimals too. And we save it in A. And here we get 1.56. And again, we can check the first 20 decimals of A. And also here we can see that 1.56 is not exactly 1.56. So the answer is here no. So there's simply no finite binary representation for 1.56, and the rounding doesn't help here actually. Next, we can also round to the next multiple of 10, 100, 1000 or whatever. And for the next multiple of 10, we would pass here -1. And consequently, for the next multiple of 1000, we have to use -3 here. And here we get 2,321,000. Now let's go on, and we have the following cash flow list. And now we have to create slices, the first 2 elements, and we can slice a sequence with inside the square brackets with a colon. And the first 2 elements is simply from the very first element until the element at index position 2, so that's the third element exclusive. Then we have the elements 300, 500, and 750, and these are at the index positions 0, 1, 2. Then we have 3 and 4. So from index position 2 till 4 inclusive means from 2 till 5 exclusive. 2 is inclusive, 5 is exclusive. Now we shall slice for the last 3 elements, and here we can use negative indexing, and from the element at index position -3 inclusive until the very last element inclusive. Here we have all elements except the last element, so from the very first element until the last element at index position -1 exclusive. And finally we have every second element starting from the very first one, so we have the first colon here which stands for all elements, and then the second colon stands for every second element. Next we shall add the cash flow 1200 for the year 7 to the list, so at the very end. And we can actually append new objects to the very end of a list with the append method. So we use the append method on the list CF, and we append the element 1200. And here we have 1200. Now in question 10 we have to change the cash flow and timestamp to, it's 300 to 400. And we have to change the list in memory, and therefore we select the element, so at index position 2, and we actually assign the new value 400. And by doing so we change the list in memory, so now we have here 400. In the next question we shall remove the last 3 years from the cash flow list, and we shall do this with slicing and variable reassignment. And therefore we slice the list for all elements except the last 3 elements, and we reassign the variable. Here we shall create a new list, CF new, with all elements of CF incremented by 20. So first of all we initiate the empty list CF new, and then we iterate over the cash flow list, and each and every element in the list we actually increment by 20, and then we append the element to the list CF new. Here we have to sort CF new from high to low, and we shall change CF new in memory. And we can do this actually with the sort method and pass true to the reverse parameter. So the sort method actually sorts in place, so it means that it changes the object in memory. And here we have now the elements from high to low. Now let's come to object mutability, and actually lists are mutable objects. So we have two projects with identical cash flows. We have the project 1 and the cash flow list 1. And actually CF2 equals CF1. And by doing so, we actually create only one object, here the list. And the variables CF1 and CF2 are both pointing or referencing to the very same object. And if you change now the very first element of CF1 to -60, then of course also CF2 references to the changed object. So let's check this here. Here in CF1 we have -60, and also CF2 is pointing or referencing still to the very same object with -60. So in this case, this was not our intention, and now we have to make sure that CF2 does not change. And we shall actually follow best practices. And therefore, first of all, we create a CF1. So this is the object. And then we create a copy of the object, which is a different object. And then we assign it to the variable CF2. So CF1 and CF2 are pointing or referencing to different objects. And therefore, if we change the object that CF1 is referencing or pointing to, then of course we do not change CF2. So here we have still -50. Alright, this was coding exercise 3. Thanks for watching, and see you in the next exercise. Bye. This is an introduction to the data type tuple. And a tuple is a collection, or more specific, a sequence like lists. So let's have a look at the type hierarchy. So here we have the collections provided by the Python standard library. And for example, we have sequences like lists, tuples, and strings. And there's actually one major difference between lists and tuples. So we have already seen that lists are mutable. And in contrast to that, the tuples are immutable objects, so they cannot be changed in memory. And typically there are very few cases where I create tuples, so I prefer lists or NumPy arrays when I need a data collection, or pandas, data frames, or series. However, it's impossible to get around tuples, as many functions and methods return data that is stored in tuples. So at least you should have seen a tuple before. Alright, let's create a list with our investment project cash flows. And we save the list in the variable CF. And we have already learned that there's the enumerate function, where we can actually create a list that contains the pair's index position and the values. So let's simply have a look here. So here we have the list stored in the variable enum. And here we have actually 1, 2, 3, 4, 5, 6 elements. And these elements are actually tuples. So you can see this here in the parentheses. So this is one tuple, and this tuple here consists of two elements, 0 and -200. So we can see that the element -200 is at index position 0, the element 20 at index position 1, and so on. And now we can also index the list enum for one tuple. So for example, for the very first one at index position 0, and we save the tuple in the variable tup. So this is here a tuple containing two elements. And we can also check here the data type, it's a tuple. And actually same as with lists, we can also index a tuple. So we can select or access single elements, and also here zero-based indexing and negative indexing applies. So if you want to get the very first element, 0 here, so this can be found at index position 0. And same as with the lists, we can index tuples by having here square brackets and passing the desired index position of the element. So here we get the element 0 at index position 0. And as I said, also negative indexing applies here. So we can also get the very last element at index position -1. So no surprise, it's -200. So indexing tuples works in the very same way as indexing lists. However, there's one major difference. And the difference is that tuples are immutable, so we cannot change or modify elements in a tuple or the tuple itself. So for example, let's assume that our initial investment is not minus 200, but only minus 150. Then we could actually index for the element that we want to change. So we select here the element at index position 1, and we could try to assign a new value, minus 150. And here we get an error message, so the tuple object does not support item assignment. So a tuple is immutable. However, a tuple has still some methods, so we can check this here after the dot with the tab key. So we have here count and index, and let's go here inside the parentheses. And here we can see that the count method returns the number of occurrences of a value. So here we can pass a value, for example, minus 200. And it's actually no surprise that we have one time the element minus 200. And there's also the second built-in method index. So let's have a look here with Shift tab. And the index method returns the first index position of a value. So here we can pass a value, for example, minus 200. And let's run the cell here. So it's no surprise that it's the index position 1. And finally, we can also extract the single elements of a tuple and save the elements in other variables. So for example, here we could say that we want to create two new variables, position and cash flow. And we can code the following. So position, comma, cash flow equals tuple. And actually now here, the very first element in our tuple is assigned to the variable position and the second element to the variable cash flow. So here we have 0 for position and minus 200 for cash flow. Next, we can also create tuples from scratch, and this works pretty much in the same way as with lists. But instead of having here square brackets, we have to pass our desired elements of our tuple within parentheses. So let's have a look here. So this is our new tuple. And there's also another way to create a tuple. So actually we do not need here the parentheses. We can simply say that we want to store and create a new tuple with the elements 0 and minus 100 in the variable top3. And this also works here. And finally, we can also convert a tuple into a list. So there's the built-in function list, and here we can pass our tuple that is stored in the variable top. So here 0 and minus 200. And it says here the built-in function list creates a built-in immutable sequence. And let's have a look here. So now here we have the list. And we can also convert a list back into a tuple with the built-in function tuple. So here we can pass the list L to the tuple function. And again, now we have here the tuple with the elements 0 and minus 200. Alright, thanks for watching, and I'll see you also in the next video. Bye. A dictionary is another data type in Python and also a data collection. So in dictionaries we can store key-value pairs, and therefore they are also called mappings. Let's have a look at an example here. And we have two lists. So we have one list with company names, Facebook, Microsoft, and Apple. And we have one list, the price, with the corresponding last stock prices. So for instance, 188.25 for Facebook and 144.61 for Microsoft. And now we want to combine the company names with the prices, and we can actually do this with a dictionary. And we can create a dictionary with curly brackets, and actually we have key value pairs. So first of all, we have to define the key, and for the first key value pair, the key is Facebook. Then we have a colon, and then we have to pass the value for the key. So in this example, 188.25. And the same we also do for the other two key value pairs, separated by commas. So let's run the cell here. And here in the output, we can see the dictionary. And actually there's no limitation on the data types. So here in the keys we have strings, and as values we have floats. And now let's save the dictionary in the variable mapping. And let's check the data type of mapping. It's a dictionary. And then we can actually access a value with the corresponding key. And we can actually do this with square brackets, and then we can pass the key. And by doing so, we get the corresponding value, 188.25 for Facebook. And actually, we can also overwrite a value or assign a new value to a key. So for instance, let's assume that the most recent Facebook price is now 190.51. Then we can do this here. So let's have a look at mapping. And now we have here the key value pair Facebook and 190.51. And we can also add additional key value pairs. So for instance, we can add Google with a recent price of 1,298. And let's have a look. So here we have on the right hand side now Google. And actually it's no surprise that also dictionaries have some built-in methods. And one method is the keys method. And here we can get actually the keys of the dictionary. So this is a dictionary keys object, but you can easily transform this into a list and get a list with the keys here. And second, there's also the method values. And similar to the keys method, here we can get the values in a so-called dictionary values object, and we save the object in the variable L. And let's check the data type. And this is a dictionary values object, but we can simply transform this object to a list or convert to a list with the built-in function list. And here we get a list with the values, so 190, 144, and so on. Next we have also the items method, and let's have a look here. And here we get a dictionary items object where the key value pairs are organized in tuples. So here we have the tuple Facebook 190.51 and so on. And we can also convert this object here to a list by using here the list function. And by doing so, we get a list with 4 tuples, and each tuple contains actually one key value pair. And we can also iterate over a dictionary items object, and actually we can unpack the tuples. So we can say for key value in mapping.items, we want to print the key value pair. And by doing so, we get here Facebook 190.51, Microsoft 144.61, and so on. And you might ask yourself if we can also use stock prices as keys and the company names as values. So this is possible as long as there are no duplicated prices. And actually the keys must be unique, and therefore the company name is the best key for a stock, as we do not have two companies with the very same name, Facebook for instance. And actually the price is not an appropriate identifier or key for a stock, as we can have the very same price for two stocks simply by chance. And we can also check this here. So we use the key Facebook 2 times and create the dictionary mapping. And actually Python only accepts the key Facebook once. So we have only one time Facebook with one value. So now let's go back to our lists. We have the stock list and the price list. And there's actually an easier way to create the dictionary. So first of all, we can create a zip object with the zip function. And we pass actually the two lists, stock and price. And this is a zip object. We can also check this here. And to understand the zip object, we can also iterate over the zip object and print all elements in the zip object. And here we get actually 3 tuples with the key value pairs. So the zip function actually organizes and stores the elements of the two lists in a way that the very first elements of the lists are actually organized in one tuple, then the second elements are organized in one tuple, and so on. And then we can transform a zip object into a dictionary with the function dict. And by doing so, we create here our dictionary. Alright, thanks for watching, and I'll see you also in the next video. Bye. We have already seen the string data type, and this is now a more detailed introduction to string objects. So let's have a look at the type hierarchy first. So these are the collections, and we have sequences, and we have mutable and immutable sequences. And actually a string object is simply a sequence containing letters, numbers, and also special characters. Obviously strings are immutable, and we can create strings by putting the sequence of characters within quotation marks. So let's have a look how it works in action. So here we have the string Facebook incorporated, and we can see that we have uppercase characters, lowercase characters. We have also special characters like white spaces and also points or dots here. So this is a sequence with characters, and we put the sequence here within quotation marks, and by doing so we create a string object. And same as with other objects, we can actually save the object in memory and assign a variable to it. So for example, company name. So here we have our variable company name, and it is referencing or pointing to the string object Facebook incorporated. And we can also check the data type, and it's no surprise it's a string object. And actually indexing and slicing strings works in the very same way as indexing and slicing lists. So also here zero-based indexing and negative indexing applies. And let's assume that we want to access the very first character here, so the capital F. Then we can pass here within the square brackets the index position 0. And let's also try to get the character at index position 3. So this is here a lowercase e. And actually white spaces or empty spaces are also characters that are part of the string. And for example, so here we have index position 0, 1, 2, 3, 4, 5, 6, 7. And here we have the white space at index position 8. And we can actually access here the white space. So here we have actually a white space or space within here the quotation marks. And also negative indexing applies, so we can actually select the very last character. It's here the point or the dot. And of course, you can also perform slicing on strings. So for example, from the third character at index position inclusive until the element at index position 7 exclusive. And here we get Cebu. Strings are immutable objects, so that means that we cannot change or modify strings in memory, and therefore if we try to get a lowercase f instead of an uppercase f, then this might not work here. So here we get an error message, a string object does not support item assignment. And actually a string can be everything. So it can contain letters, numbers, special characters, and so on. So we could also have the sentence, I invested $50 into Facebook, exclamation mark. And we saved the string here in the variable sentence. And then we can also check with the built-in function length the number of characters in, or the number of elements in the variable sentence. And here we have actually 29 elements in the string object, so including white spaces, special characters, and so on. Next, we can also convert numbers like integers or floats to strings by passing them here within quotation marks. So we have here 100, and we save here the string 100 in the variable I0, so investment, at timestamp 0. And here we can see that this must be a string, and we can also check this. So this is a string object, and of course we cannot multiply strings, for example, with 1.03, so this doesn't work. However, we can merge or concatenate strings with an plus operator. So we have here the string I0, 100 plus a US dollar. So we have here white space US dollar. And here we can actually concatenate both strings. So 100 white space US dollar. However, again, it's important to understand that here we created a new object. So the original object that is stored in I0 is still 100. And we have also the option to convert a number that is actually here a string to convert it back into an integer, for example. So with the built-in function int, then here we get 100. And also here we created a new object. So the object that the variable I0 is pointing to is still the string 100. So we have to perform here variable reassignment. And now we have here the integer 100 that is saved in the variable I0. So we can check this again here with the type function. And then again, we can convert I0 back into a string with the str built-in function. And we use variable reassignment again. And there's also the float function. And here we can convert an integer into a float. So let's do this here. So instead of having the integer 100, we have 100.0. So that's a float here. Finally, let's have a look at some useful built-in methods for strings. So for example, here we have the upper method. And actually, let's have a look here inside the parentheses. So with the upper method, we can return a copy of the string converted to uppercase. So each and every character here is uppercase now. Then we have also the method lower. So let's have a look. And the method lower returns a copy of the string converted to lowercase. So all characters should be lowercase. Next, we have the built-in method capitalize. And it says here that it returns a capitalized version of the string. So let's have a look here. So the very first character is here uppercase, and all of the other letters or characters are lowercase. And finally, we have also the built-in method title. Let's have a look here. So title returns a version of the string where each word is title cased. And title case actually means that the very first character of a word is uppercase and all of the other characters are lowercase. So here we have I, it's uppercase, then invested, the I is also uppercase, and all of the other first characters in a word are also uppercase. And here again, it's important to understand that these methods create a copy. So they create a new object and they actually do not change the original object. So our sentence is still here, the original sentence. And if we want to change this, then we have to use here variable reassignment. So let's assume that you want to have the sentence only with lowercase characters. Then we have to code the following here. So here we have the sentence in lowercase. Alright, thanks for watching, and I'll see you also in the next video. Bye. String replacement is a powerful tool that allows us to replace certain parts of strings by other values. And string replacements are in particular useful in the context of multiple printing operations, where the printed data is updated, for instance, during a for loop. So let's simply have a look how it works live in action. And we have here the interest rate, 5%. And we assume that we need to change or to update the interest rate in the near future. And now we have the string, the interest rate is curly brackets. And actually the curly brackets here mark the position in the string where we can replace or update values or characters. And we can actually do this by using the method format on the string here. And then we can pass the replacement value, so the value that we want to have here instead of the curly brackets, to the format method. So let's simply run the cell here. And here we can see that in our output, we have now the string, the interest rate is 0.05. And actually in a string, we can also have several replacements. So for example, we can also store interest rate in the variable what. And then we could have the string, the curly brackets is curly brackets. And then we use the format method. And actually the first value that we pass here within the parentheses actually is the replacement for the very first curly bracket. And the second one for the second. So let's have a look. And here we get the interest rate is 0.05. And instead of passing here variables to the format method, we can also pass the values directly. So for example, 0.05. So this is no problem. So here we have a stream of cash flows. And this is a list, for example, with 110 and so on. And we save the list in the variable CF. And now let's assume that we want to iterate over the list with a for loop. And we want to print out each and every element with a sentence, with a complete sentence. For example, the cash flow is X. And we can actually do this here by iterating over the cash flow list. And then we print the cash flow as curly brackets. And in each and every iteration or loop, we actually replace here the curly brackets by the loop variable I. So in the first loop, I is 100, and the second loop, I is 10, and so on. So let's run the cell here. And here we get the printout, the cash flow is 100, the cash flow is 10, and so on. And in addition, it could also make sense to add the timestamp of each and every cash flow. And therefore, we can use here actually two replacements. So for each and every cash flow, we could say that the cash flow is at timestamp 0, 1, 2, and so on. And actually the value of the cash flow. So we can iterate here over a range object with the length of the cash flow list. And for example, in the very first loop iteration, so I is 0, so the cash flow at timestamp 0 is, and let's have a look here, so the very first element of the cash flow list, the 100. So let's run the cell here. And here we get the cash flow at T0 is 100, the cash flow at T1 is 10, and so on. So string replacement is a pretty helpful tool. Thanks for watching, and I'll see you also in the next video. Bye. Booleans or Boolean values are the logical values true and false. And by the way, these are examples of reserved keywords in Python that shouldn't be used as variable names. So Boolean values play an important role in all programming languages and in all kind of operations and algorithms. So let's simply start, and here we have true. So we can see that here in green, this is actually a keyword here. So we can see this here. And true gives true and false gives false. And we can also check the data type of true and false. And true and false are actually instances of the class bool. So the data type is bool or boolean. However, these boolean values are also numbers. So let's have a short look at our type hierarchy. And booleans are actually also numbers. So we have integers, floats, and booleans, which are numbers. And the reason for this is that booleans can also be represented by integers. So let's go back here. And by passing true to the integer function, we can also get the integer value behind true. And this is 1. And the same we can do for false. And actually this is 0. And consequently with booleans, we can also perform arithmetic operations like with numbers. So for example, we can calculate true plus false. And this is actually 1 plus 0, which gives 1. Then we can also calculate true plus an integer, 5. And this should give 6 actually.
And of course, you can also perform subtractions, multiplications, and divisions. So for example, we could calculate false times 6. And as false is actually represented by 0, so this should give actually 0. And the same we can do also for true. So 1 times 6 should actually give 6. And that's correct. So that was a short introduction to Boolean values. Thanks for watching and see you also in the next video. Bye. In the next 2 lectures, I will show you the most frequently used operators in Python. So this lecture provides an overview on the different operator types, and in the next video we will see operators live in action. And actually we already know quite a few operators. So for instance, arithmetic operators. And for addition, we have, for example, the plus sign, and for subtraction, the minus sign, and we have star or the asterisk for multiplication, and a forward slash for division, and actually a double star or double asterisk for exponentiation. And also we have operators for modulus and floor division, but these are actually 2 less frequently used operators. Next, we have assignment operators, and we already know that with an equal sign, we can actually assign a value or a object to a variable. So for example, the integer 3 to the variable a. And we also learned variable reassignment. So for example, we can increment a by 3 or decrement a by 3 with the operator plus equal or minus equal. And the same we can also do for multiplication and division. So we can multiply a with 3, or we can divide a by 3. Then we are coming to comparison operators. And here we can actually check whether 2 objects or 2 variables that reference to objects are equal or not. And we can do this here with the double equal operator. And we can also check whether 2 objects are not equal with the not equal operator. So we have here exclamation mark equal. Then next we can check whether x is greater than y with the greater than sign. And also we have the less sign. And also we have operators for greater than or equal to and less than or equal to. Logical operators are pretty important, and here we have the operators and, or, not. And with these operators, we can actually combine statements. So for example, we have 2 statements, x less than 5 and x less than 10. And let's assume that x stands for 2, then x is less than 5 and less than 10. So both statements or all statements are true. And actually the AND operator only returns a true if all statements are true. Then we have the OR operator. And also here we can combine statements. And the OR operator returns a true if at least one statement is true. So not all, but at least one statement must be true. And finally, with the NOT operator, we can reverse the result. So instead of having false, we can reverse false and return a true. Or we can reverse true and get a false. Next, identity operations are actually not the same as comparison operators. So here we have is and is not. And they shouldn't be mixed up with equal or not equal. So here we have equal, not equal, and so this is actually not the same. So the is operator returns a true if both variables, so in this example x and y, are the same object, or if both variables are pointing or referencing to the same object. And the operator is not works in the opposite way, so it returns a true if both variables are pointing or referencing not to the same object. Then next we have membership operators in and not in. And here, for example, we can check whether a specific element is in a list. So for example, we can check whether the cash flow 100 is in the list CF. And the opposite we can check with not in.
And finally, we also have bitwise operators, and I will explain these when we come to NumPy arrays. Alright, thanks for watching, and I'll see you also in the next video. Bye. In this video, I will show you comparison logical and membership operators live in action. And let's start with the comparison operators. So let's assume we have two objects here, two cash flows, and we assign them to the variables CF1 and CF2. And then we can check whether those two are equal with a double equal sign. And of course, they are not equal. Then we can check whether they are not equal with exclamation mark equal. And this is true. Then next we can check whether 50 is greater than 60. And this is false. And then we can also check whether 50 is greater than or equal to 60. And also this is a false statement. Then we can also check whether 50 is smaller or less than 60. And this is true. And the statement 50 is less than or equal to 60 is also true. So as I mentioned before, comparison operators and identity operators are not the same. So let's have a look here. And we have a 5% interest rate stored in the variable R1. Then we assign also R1 to R2 actually. And then with the double equal sign, we can check whether R1 is equal to R2. And this should be a correct statement, as both variables are referencing to the same object, 5%. And as both variables are pointing or referencing to the same object, then the statement R1 is R2 should also give us a true. So the is operator is actually checking whether two variables, so R1 and R2, are referencing or pointing to the very same object. And the equal operator is only checking whether the objects that R1 and R2 are pointing or referencing to, whether these objects have the same values or the equal values. So let's have another example here. And we create the list with 3 cash flows. And we assign the variable CF1, and then we create a copy of the object here. And we assign the copy to the variable CF2. So we have two separate objects, and CF1 is referencing to the first list, and CF2 to the second, so a copy of the first. So we have two objects, and the objects are actually equal, so we have the same or equal values here. And therefore, if we check here whether CF1 and CF2 are referencing to equal objects or values, we get a true. But when we check whether CF1 is actually the very same object as CF2, then we should get a false. And actually is not checks the reverse statement. So whether CF1 and CF2 are not the same object. And in this case, this is a true statement. Now let's come to logical operators. And again, we have CF1, which is 50, and CF2 60. And first of all, we have the AND operator, and we can actually combine statements with an AND operator. And we only get a true if all statements are true. So we have here true, and this gives a true. So actually true and true is the same as CF1 less than 100. So this gives true. And CF2 equals 60 is also true. So here we have true, and we get a true. Then next we have true and false. And the AND operator only returns a true if all statements or all conditions are true. And here we have one true and one false. And therefore we get here a false. So here we have one true statement, CF1 is less than 100. And we have a false statement, CF2 is equal to 70. And therefore we get here a false. And also for the sake of completeness, false and false gives also a false. So now we are coming to the OR operator, so the logical OR. So we can combine statements or conditions with OR, and we actually get a true if at least one statement or condition is true. So not necessarily all statements must be true, but at least one statement. But we also get a true if all statements are true. So here in this example, true or true gives a true. So CF1 is lesser than 100. This is a true statement, and CF2 is equal to 60 is also true. And this should be here OR. So here both conditions are true, and therefore we get here a true, because at least the one statement is true. Next we have true or false, and also here we should get a true, because at least the one statement is true. And let's have an example here. So we have CF1 less than 100. This is true. Or CF2 equals 70. This is false. But at least one statement is true, and therefore we get here a true. And finally, false or false should give us a false, because no statement here is true. And finally, we also have the not operator, and this actually reverses false and true. So not false gives true, and not true gives false. So CF1 is lesser than 100 is a true statement, and not true gives us a false. And finally, this is an example where we have to use parentheses. So we have two conditions, and we combine those conditions with an AND operator. So we have CF1 less than 100 is true, and CF2 equal to 70 is false. Combined with an AND operator gives false. And then we have not false should give us a true. And actually we need to use here parentheses. Otherwise, the not operator would only reverse this statement here. And finally, let's go to membership operators. And here we have our cash flow plan, so our investment, and we save the list in CF. And with the in operator, we can actually check whether a specific element is in the list. So for example, we can check whether 20 is in CF, and this should be a true statement. And we can also check whether 30 is in CF, and this is obviously a false statement. And we can actually apply membership operators not only on lists, but also on other sequences, for example, strings. So we have here the company name Facebook, and we can check whether D is not in the company name. So here we have the operator not in, and as we can see here, so this is a correct statement, so we should get a true here. And we can also check whether an uppercase F is not in the company name. So here we have an uppercase F, so this should return a false. So these were some Python operators live in action. Thanks for watching, and I'll see you also in the next video. Bye. Hi and welcome to coding exercise 4. We are here on the Jupyter dashboard, and we have the course materials on the desktop. Course materials part 1. And we go to exercises, and now we go to exercise 4. And exercise 4 covers tuples, dictionaries, strings, booleans, and operators. So first of all, we have to create a tuple and index a tuple for an element. And then we try to change an element in a tuple. Then we create a dictionary and return a value for a key. And then we iterate over the dictionary and print all key value pairs. Then we have a string, and we shall index the string for the second last character and also convert the string to uppercase. Next we have A and B, and we should check whether A is greater than B. And then we have C and D, and we should check whether C is not equal to D. Here we should check whether two variables are referencing to lists that are equal, and also whether two variables are referencing or pointing to the very same list, or to say to the very same object. And then we have here two conditions, condition 1 and condition 2, and we should check whether at least the one condition is met, So here we have to use a logical AND, OR, and NOT. And here we have to check whether both conditions are met. So we have the conditions 3 and 4. And finally, this is a more complex statement. And before you run the cell, you should verify whether this code returns a true or a false. Alright, this is coding exercise 4, and if you want to do it on your own, then please stop the video now. Alright, now let's go to the solution. And first of all, we have to create a tuple with the elements 100, 3%, and 103. And we can do this by passing the elements within the parentheses here and separate it by commas. But actually, we do not need the parentheses here. So let's have a look. So here we have a tuple. And same as with the lists, we can also index the tuple, for instance, for the second element at index position 1. And we can also try to change or mutate an element in a tuple, for instance, changing the third element to 106.09. But actually this does not work, as tuples are immutable objects. Next, we can store key-value pairs in a dictionary, and we have a so-called mapping. And here we shall create and save a dictionary with two country capital pairs of our choice. So for instance, France and Paris. And here we open the curly brackets and we have the keys France and Italy and the values Paris and Rome. And then we can get the capital of France by passing the key within the square brackets here, and we get the corresponding value. It's Paris. And then we can also iterate over the dictionary and print each and every key value pair. And here we also have to use string replacement. So for each key value pair, we should use x, y, z as the capital of ABC. And first of all, we transform each and every key value pair into a tuple with the items method. And then we unpack the tuple with key comma value. And we do this for each and every key value pair. And then we use here string replacement, and we have two curly brackets. And the first curly bracket is replaced by the value, and the second by the key. And here we have Paris is the capital of France, and Rome is the capital of Italy. Here in question 7, we have the following string, and we can save the string in the variable stat for statement. And then we can also index a string, for instance, for the second last character, and it should be an R. So the dot or the point is the very last character. And then we can also convert a string to uppercase. So we can convert each and every character to uppercase with the upper method. And we actually reassign the variable. And now we have the statement in uppercase letters. Now here we have A and B, and we should check whether A is greater than B. So first of all, let's create A and B. And we can also print A and B to check this manually. So actually A is obviously less than B, and therefore we should get here a false. Next we have C and D, and first of all we create a C and D. And then we should check whether C is not equal to D, and we can do this with exclamation mark equal. And here we get a false, and this means that C and D are equal, and we can also check this. So this is the very same value here. Now in the following we have the list CF1, then we have CF2, which is actually the same as CF1. And actually CF2 is referencing or pointing to the very same object. And then we have CF3, which has the same values in the list, but this list is a different object. And if you check now whether CF1 and CF2 are equal, so with the double equal sign, then we check whether the objects that CF1 and CF2 are referencing or pointing to have equal values. And this is the case. And actually CF1 and CF2 are not only equal, but actually also the same. So they're referencing to the very same object. In question 12, we now have to check whether CF3 and CF2 are referencing to the very same object. And we can check this with the is keyword. And obviously this is not the case. So CF3 is referencing to an object with equal values, but the object is not the very same object that CF2 is referencing to. So let's check this here. And here we get a false. Now here in the following we have two conditions, condition 1 and condition 2. And condition 1 checks whether this number here is divisible by 3. And condition 2 checks whether this number is greater than 63 times 650. So let's create the two conditions. And for each condition we should actually get a true or a false. And if our task is now to check whether at least one condition is met, so at least one means a logical OR. So we can check this with the keyword OR. And here we get a true, and let's print condition 1 and condition 2. And condition 1 is false, so this number is not divisible by 3. And condition 2 is true. And therefore at least one condition is met, and therefore we get here a true. Next we shall check whether both conditions are met, and we have here conditions 3. So this number is divisible by 7 or not. And we have condition 4. So let's create both conditions, and we get true or false. And now if you want to check whether both conditions are met, we have to use the AND keyword. And we get a true here, and therefore we can say that condition 3 is true and condition 4 is true. Finally, we shall check whether the following code returns true or false. And let's have a look here. So first of all, we have type 23 equals integer, so this is an integer 23. And therefore within this parenthesis we get a true. Then we have here not true is false, so this is a false. Then we have 4 unequal to 3, this is true. And therefore we have here true or false. And true or false gives a true, and not true gives a false. So let's have a look here. And this is correct. Alright, this was coding exercise 4, and hope to see you also in the next exercise. Bye. In this video I'm going to introduce conditional statements and the keywords if, elif and else. So far we were able to check whether a statement is true or false with comparison operators. So for example we can check whether the second element in our cash flow list is greater than 0. So 20 is greater than 0, this is true. But very often it is the case that you want to take a particular action if a condition is true. And if the condition is false or not met, you want to take a different action. And in Python we can do this with if, elif and else. So let's start with if. So this is a Python keyword. You can see this in green. And then we copy here our condition. And we paste it here. And then we use a colon. So we check whether the second element is greater than 0, and then we press the enter key. And by default you can see here that Python creates an indent. And now we can define an action that we want to take in case that the condition here is true. So for example we could print the string is positive or positive. And let's run the cell here. And here we get as output positive, because the statement here is true, and therefore the action here is executed. Alright, now let's do the same also for the very first element, minus 200. At index position 0. And this is a false statement, and therefore the action here, printing positive, is actually not executed. However, let's assume now that if the condition here is not met, we want to take an alternative action. So for example, printing a negative, and we can define this here. So we can now use the Python keyword else. And also here we have to code a colon and press return. And also here we get automatically an indent. And here we can define now the alternative action in cases where the condition here is not met. And in our case, maybe it's printing a negative. And let's run the cell here. And here we get the output negative. And actually we can do this for all elements in our list. So we can iterate over the list and check for each and every cash flow whether the cash flow is positive or negative. And of course we can do this with a for loop. So let's create the for loop here. So for I in CF, and then we copy here our if and else statement. And it's actually important here to make the right indent. So we have here after the for loop an indent. Then here we need an indent after the if statement. And also here we have to make the right indent for the else statement. So it must have the same indents than the if statement. And we also have to press here the tab key for the printing. And finally we have to replace this here by the for loop variable I. And let's run the cell here. And here we get negative, positive, 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 positive. So we have minus 200 is negative and all of the other cash flows are positive. So here we have the combination of a for loop and conditional statements, and this is very commonly or frequently used. So we iterate over a list or sequence and check for each and every element whether the element fulfills a certain condition, and then we define actually the actions to take. So now let's go on here. And of course we can also have more advanced actions, so we can use here a string replacement. And in case that the cash flow is positive, we can print the cash flow is a positive cash flow. And we can actually replace here, or we can insert here the particular cash flow into our action or into our string. So let's run the cell here. So minus 200 is a negative cash flow, 20 is a positive cash flow, and so on. So far we considered two different cases. So either a cash flow is negative or a cash flow is positive. And now let's assume that we have a cash flow of 0 in one particular year. So we can actually do this here by inserting the value 0 before index position 3 with the insert method. And let's check CF again. So here we have the value 0 now. And consequently we have three cases. So we have the case that the cash flow is positive. Then we have the case that the cash flow is negative. And we have the third case that we have no cash flow at all. And actually we can cover multiple cases with elif. So again we iterate over the cash flow list. And first of all we check whether the cash flow is positive. And if the cash flow is positive, then we print cash flow is positive. Then we check the second case with the elif statement. So if the cash flow is not positive, then please check whether the cash flow is negative. And if this is the case, please print the cash flow is negative. And in all other cases, so the cash flow is neither positive nor negative, then else print no cash flow. So let's run the cell here. And here we get minus 200 is a negative cash flow, 20 is a positive cash flow, and here we have a no cash flow. And instead of having here a combination of if, elif, and else, we can also make this more explicit. So here with the else statement, we cover all other statements that are not covered by the if and elif statements. So in this case, the case that the cash flow is 0 is the only alternative case here. But also here we can do this more explicit, and we can iterate here again over our cash flow list and print a positive cash flow if the cash flow is greater than 0. Then we can print negative cash flow if the cash flow is less than 0. And then we can check for the explicit case also with an elif statement. So elif I equals 0, then we should print no cash flow. And this gives in this example here the same result as above. And actually the number of elif statements is not limited. So theoretically we could have here
10 or 20 elif statements and check for 10 or 20 different cases. Next, let's further extend our case here, and let's assume that we want to put all negative cash flows in a new list and all positive cash flows in a list. And therefore, we can create here the two empty lists, cash flow positive and cash flow negative. And then we iterate over the cash flow list. And if the cash flow is positive, then we append the cash flow in the list or to the list the cash flow positive. And else we append the cash flow to the list cash flow negative. And finally, we print out both lists here. So here we have the list cash flow positive with the elements 20, 50, 70, 100, and 50. And we have the list cash flow negative with minus 200 and 0. And actually we have also 0 here in the list the cash flow negative because we used here the else statement. And else in this case also covers I equals 0. And therefore alternatively we could use here elif. So we only put positive cash flows in the list CF positive and all negative cash flows less than 0 in the list cash flow negative. And now we only have minus 200 in the list cash flow negative. All right, thanks for watching, and I'll see you also in the next video. Bye. The keywords pass, continue, and break are pretty useful and extend our options and functionalities when working with conditional statements. So let's have a look at some examples. And again, here we have our cash flow projection, where we also have 0 cash flows in 1 year. And in the last video, we learned how to create 2 new lists, one list with only positive cash flows and one with negative cash flows. So we checked here for each and every element whether the element is positive or negative. And it actually returned a list with positive elements and a list with negative elements. However, the element 0 is in no list here, so it's neither in the positive list nor in the negative list. So the element 0 neither fulfills the first condition nor the last condition. And the default behavior is if we do not define here an else statement, then by default the action is actually a no action. And we can actually make this more explicit by defining here an else statement. So we can define that in all other cases we want to do nothing, and actually we cannot simply leave here a blank line for no action, but still we can actually define here a no action, and we can do this with the keyword pass. And of course the result does not change here. So we get here the positive cash flows and here the negative cash flows. And for 0 we defined that the Python should do nothing by having here the pass statement. And as I said before, this is the default behavior. So if we do not define any alternative action here at all, so if we do not define here else, then by default Python does actually nothing. So here in this case it's not required to have here the else statement with pass. But now let's assume that first of all we want to check whether the elements are equal to 0. Then also here we cannot simply leave the action blank. So this does not work. And also if we create here the action line here. And also in this case we have to define an action, and even if it's the no action, so we have to define it. And we can do this with the pass keyword. So if the element is equal to 0, then Python should do nothing. If the element is greater than 0, then the element should be appended in the list CF positive and in all other cases. So in the case that the cash flow is negative, then the cash flow should be appended to the list CF negative. And of course, this gives here the same result. However, there's one thing that I want to show you, and where you have to be careful when you use the pass keyword. So this is essentially the very same code, but instead of having here only one line with pass for the action,
in case I is equal to 0. So we have another line here printing this is 0. And it's important to understand that even if we have here pass, so do nothing, then Python nevertheless goes into the next line here and checks the other actions. So let's run the cell here. And in this case, so the statement this is 0 is executed here. And then all of the other elements are correctly located here in the respective lists. So printing the statement here, this is 0, is not really helpful. And what we actually wanted to do here, we wanted to check whether the element is equal to 0. And if this is the case, then our intention might be that Python immediately goes to the next element and actually stops to evaluate the current element or value. And instead of having pass here, where the next actions are still evaluated, instead of having pass, we can also have here the keyword continue. And by having here continue, Python directly stops the iteration and goes to the next element in the cash flow list. So let's run the cell here. And here we do not have the statement this is 0. Because once we come to the element 0 in our iteration, then the statement here is true. And the very next action is continue. And continue means that we stop the current iteration or element, and we immediately go to the next element in our for loop. And the next action, so printing this is 0, is not evaluated or considered anymore. So that's the functionality of continue. Now let's consider an investment where we have in the first 4 years negative cash flows. So typically startups and very new companies have negative cash flows not only in the very first year, but also in the second, third, or fourth year. So this is actually a very common example or a very common cash flow projection for a startup company. And then at some point in time, it turns positive and grows. So let's define here the list CF. And now let's assume that we want to determine the first year where we have positive cash flows. So the first profitable year. And in this case, it's year 0, 1, 2, 3, 4. So it should be year 4. And there are actually 2 alternatives how to do this. So the first alternative, we create here the variable n. So that's the number of years, and the initial value is the 0. And then we iterate over the cash flow list. And if the respective cash flow is positive, then we print the year XYZ is the first profitable year. And we replace here the curly brackets by n. And then at the end of each iteration, we increment n by 1. And then we go to the next element and so on. So let's run the cell here. And here we actually have year 4 is the first profitable year. Year 5 is the first profitable year, and so on. So actually our iteration does not stop after the first profitable year. And actually for all years following year 4, we have the statement this is the first profitable year, which is actually incorrect. So in this case here, we want to break or to stop the iteration once a condition is met. So once we have found a cash flow that is positive. And we can actually do this with the keyword break. So let's include here in our if statement as additional action the keyword break. And break means that we completely stop the for loop and the iteration. So once we have found a cash flow that is positive, then we print the year XYZ is the first profitable year. And the next action would be that we completely break our iteration. So let's run the cell here. And here we get only year 4 as the first profitable year. So let's again have a look how the iteration works in detail. So the very first element is minus 200. Then we check whether minus 200 is greater than 0. And this is false. And therefore, neither the action print nor the action break is executed here. And then as very last action in the first iteration, we increment n by 1. So we have n equals 1. Then we go to the next element, minus 100. And also here the condition is false, and we jump to the increment, and we increment n to 2, and so on. And there's actually also a second alternative how to do this. So we do not necessarily need to work with the variable n. And we can actually iterate over a range object with the length of the cash flow list, so 10 elements. So we iterate here from 0 till 9 inclusive. So for example, in the very first iteration, we check the element at index position 0. It's minus 200, whether minus 200 is greater than 0. And this is of course false. So the following actions are not executed, and we jump to the next iteration. And once we have reached 20, then this statement here is true, and we print out year 4 as the first profitable year, and then we break the whole iteration or the whole for loop. And of course here we get the very same result. Alright, thanks for watching, and I'll see you also in the next video. Bye. In this lecture we will apply our new skills to determine an investment project's payback period. So the payback period of an investment is simply the time until the initial investment is recovered. So we start at the initial investment, which is a negative cash flow, and then we add the cash flow of the first year. So to say, we calculate the cumulative cash flows, and we will continue to do so until the cumulated cash flow is greater than 0. And this is also called the break-even point of an investment. So again, here we have the XYZ company that buys an additional machine for 200, and we have some positive cash flows. So let's create the CF list. And then we create the variable accumulated cash flow, and the initial value is 0. Then we iterate over the cash flow list. So for I in range, the length of the cash flow list, so from 0 till actually 5 inclusive. And for each loop or for each iteration, we have 3 actions. So first of all, we increment the accumulated cash flow by the cash flow of the respective iteration. So for example, in the very first iteration, it's minus 200. Then here we could also print the intermediate result, the accumulated cash flow. And then third, we check whether the accumulated cash flow is greater than 0. And if this is the case, then we print the statement, the project's payback period is XYZ years. So we replace here the curly brackets by I. And actually once accumulated cash flows is greater than 0, we break here our iteration and our for loop. So let's run the cell here. And here we get the intermediate results, the accumulated cash flow. So after the first iteration, it's minus 200, then minus 180, so minus 200 plus 20. Then plus 50 gives minus 130 and so on. And finally, after 4 years, we have a positive accumulated cash flow of 40, and we print the statement, the project's payback period is 4 years. And then we have a break here. So this works here. However, we should also define an action for the case that a project does not break even. So let's assume the next project here. So here we have minus 200 and minus 150 in the first 1 or 2 years. And obviously this project does not break even. So here the sum of the positive cash flows is less than the sum of the negative cash flows. So again, we create the variable accumulated cash flow, and we iterate over the cash flow list. And actually until here it's the same. And then we add an elif statement. And here we check whether the accumulated cash flow is less than or equal to 0. And so we can combine here 2 or many statements with and or. So we can only say that the project does not break even once the project has terminated after the very last cash flow, so here 50. So 2 conditions must be met. The accumulated cash flow must be less than or equal to 0, and we actually must have evaluated the very last element. So I equals the length of the cash flow list minus 1. So in this case, I equals 5, so the very last iteration. And let's run the cell here. And here we get the project that does not break even. And of course, we do not have to print the intermediate results, so we can actually cross this out here. And we only get the project does not break even, and same we can do here. So we can actually cross the intermediate printing. And let's finally check if this code still works for a project that does break even. So CF is the project that does break even, and let's run here the cell. And here we get the project's payback period is 4 years. Alright, thanks for watching, and I'll see you also in the next video. Bye. This is an introduction to while loops, a very powerful tool in Python. And to show you when and why we should use a while loop, I will use in this lecture a toy example. So let's assume we have two integers, a and b, and we do not know the values of a and b. However, we do know that a is greater than b. And the plan is now actually to decrement a by 1 until a is equal to b. And in addition, we want to determine the difference between a and b. So let's define a and b. A is equal to 10 and b is equal to 5. However, we do not know this. So we only know that a is greater than b. And then we create a new variable, difference, and the initial value is 0. And then we can check whether a is greater than b with a conditional statement. And if this is the case, we print out a tuple, a and b, and also the string or the statement a is still greater than b. And then next we decrement a by 1, and we increment the difference by 1. And we will repeat this process until a is not greater than b, so until a is equal to b. And if a is equal to b, then we print out the differences, and actually here the final value that is stored in the variable difference. So let's run the cell. And this is actually the very first iteration. So a is 10 and b is 5. And the statement is a is still greater than b. And we actually decreased a by 1 and increased the difference by 1. So let's take here the next iteration. And now we have a equals 9 and b equals 5. And of course, a is still greater than b. So now let's repeat here the process, and let's rerun the cell until a is equal to b. So finally, we have here the result, the difference is 5. And if we print out now a and b, then we get here 5 and 5. So we solved the problem here. However, it is not really efficient to rerun cells. And so we have here many loops. And whenever we have many loops, we could also use a for loop. So again, we have a equals 10, b equals 5. And the initial value for difference is 0. And then we use here a for loop. So for e in range 6, and in total here we have now 6 iterations or loops. And then we check whether a is greater than b, and print out a and b, and decrement a and increment the difference. And once a is equal to b, then we print out the difference is here the difference. So let's run the cell here. So here we have 10, 5, a is still greater than b, and some more iterations, and finally we end up with the difference is 5, and a is also 5. So the for loop does the job here. However, there's one problem actually. So we do not know the difference between a and b, and therefore we do not know in advance how many iterations or loops we actually require or need. So I passed here 6 to the range function because I knew that in the end we require 6 iterations, but typically we do not know this in advance. So for example, if we specify 9 loops, then we have 4 times, so the difference is 5. So we have more iterations or loops than necessary. And in this case, we could actually solve the problem by using here a break keyword. So once the difference is 0, we break here the loop. But still, let's assume that our initial guess is that we need 4 loops. Then actually we do not reach the end or the desired result of our task here. So A is still greater than B, and we do not know the difference between A and B. And here comes the while loop into play. And the while loop is a so-called indefinite iteration or loop. And in contrast to that, the for loop is a definite iteration or loop, because the number of loops are specified explicitly at the time when the loop starts. And in contrast to that, in a while loop, the number of times the loop is executed isn't specified explicitly in advance. And rather, the while loop runs as long as some condition is met. So with a while loop, we can decrement A by 1 and increment the difference by 1 until A is equal to B. So again, we have A equals to 10 and B equals to 5, and the initial value for the difference is 0. And then we use a while loop, and we start with the Python keyword while, and we say while A is greater than B, colon. And for our intuition, we could also say that as long as A is greater than B, and then Python makes automatically an indent here. And here we can define the action that we want to take. So we want to print out A and B and say that A is still greater than B. And also we want to decrement A by 1 and increment the difference by 1. And finally, once the while loop has stopped, we want to print out the final value of the difference. So let's run the cell here. And actually we can see here that we have 6 iterations. So we have 10, 5, 9, 5, 8, 5, and finally we have the difference is 5. And actually A is also now 5. So that's the main intuition behind a while loop. However, there's one major pitfall. And let's have again the same case. A equals 10, B equals 5, and difference is 0. And instead of decreasing A by 1 in each step, we made a mistake here and we increase A by 1. So actually A will never be 5. So in the next step, A will be 11, then A will be 12. But A will never reach the value 5. And let's run the cell here. And we can see that we have many loops. So in theory, we have an indefinite amount of loops, and therefore we have to cancel or to quit here the kernel or interrupt, and we can do this here with interrupt. So otherwise our code is running forever actually. So let's go to the very end, and here we can see that we have interrupted the code. So finally we had here over 130,000 loops. That's the pitfall here with the while loops. So we only made a small mistake and actually we created an infinite loop. Alright, thanks for watching, and I'll see you also in the next video. Bye. In this lecture we are going to create our very first user-defined function. And user-defined functions help us to organize code, and if you want to reuse a code fragment again and again, it might make sense to organize the code in a reusable function. For instance, let's assume that we have a code fragment with 20 lines of code and we need to reuse it many times. So this is getting really messy, and this is one case where we should create a function. And typically functions also enhance the readability of our code to others, as you can give a meaningful function name and then everybody understands what you are doing. So let's have a simple example here, and we have already learned how to calculate the future value given the present value, the interest rate, and the number of periods. And with the following code and the following formula, we can calculate the future value. So here we have 121. And this is based on a period of 5 years. but let's change it to 6 years, and therefore we have to change here the parameter n, and we have to rerun the line where we calculate the future value. And actually it would be more comfortable to have here a function, so for instance the future value function, where we have the 3 parameters, present value, interest rate, and number of periods. And then we can simply pass our arguments here within the function. So this would be great, but there's no future value function, and therefore we will create our very own user-defined function. And we can actually do this with the def keyword. And then we can define the function name. So in this case, for instance, it's a future value. And here you can see in blue the function name, and there are actually some conventions. So for a function name, you should use lowercase letters, like here, future value. And then we can specify some parameters by opening the parentheses. And we have here present value, the interest rate, and the number of periods. So let's define the parameters here. We have a present value, then we have the rate, and we have the number of periods. And then we need a colon. So this is the function header where we define the function name and the parameters. And then we press enter. And Python automatically makes an indent here. And now we have to define the action or the calculations that the function shall perform. And in our case, it's calculating the future value. So let's copy here the formula. And we have actually the parameter present value, then we have rate. And we have number of periods. And here within the function, based on present value, rate, and number of periods, we calculate the future value. And we create here the function variable future value. And finally, our function should return the future value that we calculated. And we can do this with the return keyword. And then we want to return the future value. So this is our very first user-defined function. So we defined the function here in the header, and we defined the actions in the body, and finally we return the result of the function, the future value. And finally we can define the function by simply running the cell. So now we have defined the function, and in a very next step we can actually call the function by passing some arguments to the parameters here. So let's do this here. And actually we can call the function by simply writing here the function name, future value, and then we can open the parentheses. And then we have to pass the values or the arguments that you want to have to the parameters present value, rate, and number of periods. So let's run the cell here and let's call the function. And here we get the result 121.66. And if you want to change now the number of periods to 6, then we can simply do this here. And we can actually rerun and reuse the code. And here we get 126.53. So the function future value returns the future value here. And we can see this here in the output. However, in many cases, we want to store the result of a function in a variable. And of course, we can do this. So here on the right-hand side of the equal sign, we actually call our function future value. And we assign, or we store the result in the variable future value. And here we have 121. And finally, there's no need to pass the numbers here to the parameters. So 104% and 6 or 5 years. So we can also pass here the variables that we defined here. And these variables are pointing or referencing to the objects. So we can also pass here the present value that we saved here to the function parameter or variable PV. Then we can pass R to the rate parameter and N to the NPER parameter. And also here we get the result 126.53. So here N is 6. Alright, this was the very first user-defined function. Thanks for watching and see you in the next video. Bye. Alright, we have already learned the difference between a function parameter and a function argument. And many people mix up these terms and use them interchangeably, and also I do. But that's not a problem, as everybody understands what you mean. But we should keep in mind that there's a slight difference. And let's have a look at our future value function. So we have the parameters, the present value, rate, and nper. So these are the function parameters, or also function variables. And then we actually pass the arguments or the values 100, 4%, and 5 to the parameters. And actually even more important is the difference between keyword arguments or named arguments and positional arguments. And let's again define our future value function. And first of all, we can simply call the function by passing 100, 4%, and 5 in this sequence here. So we have the present value 100, then we have the interest rate of 4%, and we have 5 periods. And actually these arguments are also called positional arguments. So we pass the arguments in the sequence, in the very same sequence of the parameters, and we can do so. And here we get the correct result 121.6. However, when using positional arguments only, so we have to keep in mind that the sequence or the position matters. So we have to pass the positional arguments in the very same sequence as the parameters. And if we mix these up, so for instance, first of all, we pass 4%, then 100, and then 5. Then our function uses the present value 4%, the interest rate 100, and 5 periods. And consequently, we get here a false result. So these are so-called positional arguments, and the sequence matters. And the second alternative is that we can actually use keyword arguments. And in this example, we use keyword arguments only. So we explicitly pass here 100 to PV, then we pass 4% to the parameter rate, and we pass 5 to the nper parameter. So these are called keyword arguments, as we explicitly passed the arguments with an equal sign to the parameters. And actually when using keyword arguments, there's one advantage, so the sequence does not matter. So if we first of all pass 4% to the rate parameter, then 5 to the nper parameter, and finally 100 to the present value parameter, then this works. Because Python exactly knows what we want to do here. And this is actually not the case with positional arguments. So here Python assumes that we pass 4% to present value, and in this case it's not correct. So for positional arguments, sequence matters, and for keyword arguments, the sequence actually does not matter. Next, we can also use a combination of positional arguments and keyword arguments, and this is actually the most common case. So I typically use a combination, and typically the first parameter or the first two parameters of a function or a method are the most important parameters. And for most functions or methods, I simply know the position of the most important parameters. And therefore, so let's assume here for the future value function, the most important parameter is actually the present value. And here I pass 100 to present value, and this is a positional argument. And then I start with the keyword arguments. So I use the keyword argument 4% to the rate parameter, and I use the keyword argument 5, and I pass 5 to the nper parameter. And this works. And of course, I can also have two positional arguments. So I can pass 100 and 4%. And finally, the last argument is then a keyword argument. So this works. But when using a combination of positional and keyword arguments, there's one important rule. So once we use our very first keyword argument, so for instance rate, then after that we cannot use positional arguments anymore. So once we start with keyword arguments, then we have to proceed with keyword arguments. And for instance, this example here does not work. So we have a positional argument, then we have a keyword argument, And then we have another positional argument, and let's try to run the cell here. And here we get an error message, so positional argument follows a keyword argument. So here we used a keyword argument for the very first time, and after that we cannot use positional arguments, so this is a pretty simple rule. So in this example, what's the correct code? And we start with the positional argument 100, then we use the keyword argument 4%, and after that we have to use another keyword argument. So we have to explicitly pass 5 to the nper parameter. And this works. Alright, thanks for watching, and I'll see you also in the next video. Bye. Alright, we still have our future value function, now called future value 1, with the 3 parameters, the present value, interest rate, and number of periods. And then we can call the function by using either positional or keyword arguments. And actually here all arguments are mandatory arguments. So Python expects that we pass 3 arguments here, and if we do not pass all arguments, so let's try this out, and let's pass only 2 arguments, then Python assumes that 100 is for the present value, 4% for the interest rate, but we get here the error message that we have one missing required positional argument, numbers of periods. And actually Python simply does not know what to do and what to use for number of periods here in the function and in the calculation. However, we can set and determine default arguments, and these arguments are automatically used if we do not specify an argument. And actually working with default arguments makes sense whenever we can specify a default argument that is typically or in most cases used for this function and for this parameter. So let's have an example here. With our future value function, we assume annual compounding, so a compounding period of 1 year. However, we have already learned that sometimes we have quarterly or even monthly compounding frequency, and actually our function should provide this additional functionality, and therefore we should add the additional parameter m with the number of compounding periods per year. And also here we have 2 options, and let's have a look at the first option. So we can define m as a mandatory argument, so we have to specify m. And we can simply do this by having here our future value 2 function, and we add the parameter m. And also here in the function body we add m respectively. So let's define future value 2. And then again we can call the function future value 2. And for instance we can pass the argument 1 to the m parameter. So that means that we have annual compounding. And here we get the same result as before. So before we implicitly assumed that m is equal to 1. But we can also calculate the future value with quarterly compounding by passing 4 to the m parameter. And here the future value is slightly higher because we earn interest on interest, so compound interest on a quarterly basis. And then we can also assume monthly compounding by passing 12 to the m parameter. And here we get even a higher future value, 122.09. So this is the first alternative how to add the additional parameter m. And as I said before, so m, the argument m is mandatory. And if we forget to specify m, then we get here an error message and it says missing one required positional argument m. And now let's come to the second alternative, and actually we can define a default argument for m, and typically we assume an annual compounding frequency, so the default argument could be 1 for the parameter m, and we can specify this for the function future value 3, so we have the parameter m equals 1, so this is the default argument, and let's define the function here. And consequently, if we are happy with the default argument, so if we assume annual compounding, then we do not have to specify m, and we can simply pass only 3 arguments for present value, rate, and number of years. However, if we want to change m, then we have to explicitly define an argument. So either we can use a positional argument by having here 4 positional arguments, and we pass actually 12. So we have monthly compounding and get 122. And of course, we can also use a keyword argument, and we can explicitly pass 12 to the m parameter. And of course, this gives the very same result. Finally, there's one important thing that you should know when defining default parameters or default arguments. So let's have a look at future value for the function. And here we specify the parameter present value, rate. Then we have the default parameter or argument m. And finally, after that, we have the mandatory argument, the number of years. And let's try to define the function here. And here we get an error message, and it says a non-default argument follows the default argument. So once we have defined one default argument or parameter, then all of the following arguments must also be default arguments. Or to put it the other way around, so the default arguments must be the very last arguments of our function. Alright, thanks for watching, and I'll see you also in the next video. Bye. It might be the case that you have already seen the default argument none in a function or a method. This is not uncommon, and in this lecture, I want to give you an intuition why and how this is used. Typically, when we have the default argument none in a function or method, then the real default argument is specified in the function body, like in this case here. So if you do not specify m, then the function uses the default value 1. And let's have a short excursus on the none object. So we have none, and we save the object in the variable a. And actually a produces an output of nothing, so it's simply none. And we can also check the data type. It's a none type. And if we pass none to the bool function, then we get a false. And consequently not a gives a true. So if we have here the following code, if not m, so if we do not specify m, then the function uses the default value 1. And otherwise, if we specify a value for m, then the function uses our value. So let's define the function future value 5. And actually it produces the very same results as before with the default argument m equals 1. So let's call future value 5 with the default argument. And here we get 121.66. But of course we can also explicitly pass an argument, for instance 12 for monthly compounding frequency. And here we get 122.09. So the question is now, what is the difference and the benefits of using none? And there's actually a small but pretty important difference. And let's assume that we are working in a bank and we set the compounding policy for ordinary savings accounts. So here we specify an annual compounding frequency. So by passing 1 to compounding policy. Now we have the future value 6 function that allows to calculate the future value for savings accounts based on the present value, the interest rate, the number of years, and also the compounding policy. And the policy for ordinary retail accounts is annual, but for very few privileged business clients, we also have savings accounts with a monthly compounding frequency, and therefore we have the parameter m with the default argument compounding policy. So let's define the function future value 6. And let's calculate the future value for one retail account with the present value 100. And the interest rate is 4%, and we have 5 years. And we get 121.66. And now let's assume that we change the compounding policy for retail accounts from annual to, for instance, monthly. Now let's call again future value 6 with the default argument. And we would expect that now the default argument is 12. So let's run the cell here. And we would expect actually a future value of 122. But still we get 121.66. based on a compounding policy of still actually annual, so 1. So we actually didn't change the default argument for our future value 6 function, even if we changed here the compounding policy. So we set the default argument m equals 1 for the function future value 6 at the time when we define the function. And at that time, the compounding policy was 1. And this is fixed unless we redefine the function and rerun the cell here. But that's pretty inconvenient. And therefore, there's a better solution with the default argument none. So let's define future value 7 with the default argument none, specifying in the function body the real default value that is equal to the compounding policy, to the current compounding policy. And actually, when specifying the default value in the function body, the value is specified in that moment where we call the function. And in contrast to that, if we specify the default argument in the function header, then the default argument is set in that moment where we define the function, and we cannot change it anymore unless we redefine the function. So that's the difference, and let's now define future value 7. And first of all, let's assume that our initial compounding policy was 1, so annual. And now let's redefine here. And let's call the function future value 7 with the default argument. And here we get 121. And now let's assume that we change the compounding policy to 12. And actually, we do not need to rerun or redefine the future value 7 function. We can simply call the function. And here we get the result 122.09. And that is based on the revised compounding policy and the changed default argument of 12. So the key message is here that whenever we want to have default arguments that should be dynamic and that should be changed after we defined the function, then we should use the default argument none. And then we specify actually the real value, the real default value in the function body. Alright, thanks for watching, and I'll see you also in the next video. Bye. This is a short repetition on how to unpack iterables like tuples or lists, and then I will show you how to work with the so-called star args expression. So this lecture covers some basics that we require before I can introduce the function parameter star args in the next lecture. And let's assume we have a tuple with 4 elements, 1, 2, 3, 4, and then we can unpack the tuple by having here a, b, c, d equals tuple. And by doing so, we store the element 1 in the variable a, the element 2 in the variable b, and so on. So let's check this. So a is 1, b is 2, c is 3, and d is 4. And actually something similar happens when positional arguments are passed to a function. So let's consider here our function future value 2 with 4 parameters, the present value, rate, the number of years, and m. And then we can call the function with 4 positional arguments, 100%, 5 years, and 12 periods. And let me show you what happens in the background. So by passing 4 positional arguments, we actually pass a tuple with 4 elements. So this is the tuple here. And then actually the function unpacks the tuple and assigns to the very first parameter the first value of our tuple, to the second parameter the second value, and so on. So this is what happens in the background. So PV, rate, number of years, and m equals tuple, and we actually unpack the tuple. And we have for the present value 100, for the interest rate 4%, for the number of years we have 5, and we have m equals 12. So now let's go on and let's have the tuple with 4 elements, 1, 2, 3, and 4. And then we can also unpack the tuple with the following code, a, star b equals tuple. So let's have a look here. We have a, which is 1, and then we have b with the remaining elements. And also with this expression here, we unpack the tuple, and we assign the very first element, so 1, to A, and then star B exhausts all remaining elements. And the important part is here actually the star sign, so let's delete it here. And here it says there are too many values to unpack. So we have only 2 variables, but we have 4 values in our tuple, and this doesn't work. So we use here the star operator actually. And by doing so, star B exhausts all remaining elements. Now let's have another example, and let's have the list with 4 elements, 5, 6, 7, and 8. And then we can unpack the list with C, D, star E. And it's actually no surprise that we assign 5 to C, 6 to D, and the remaining elements 7 and 8 to E. Let's check this here. So we have 5, we have 6, and we have the remaining elements here in a list for E, 7 and 8. And typically the convention is that we use star args. So this can be any name, but typically we use args. And in particular, when we use this in functions as function parameter, so we will see this in the next lecture. So typically we have this here, so C, D, star args. And by doing so, we unpack the list, so the result is actually the very same. We have 5, 6, and the remaining elements. And now let's have a final example. So we have still my list, and we can actually change the sequence here, and we can start with the expression star args, C, D. And actually Python assigns the last element 8 to D, the second last element 7 to C, and all remaining elements are then actually stored in args. So here we have args with 5 and 6, then C with 7 and D with 8. Alright, thanks for watching, and I'll see you also in the next video. Bye. In this lecture I will show you that we can also pass a sequence like a list to a function parameter, and I will also show you how to use star args in a function. And star args allows us to pass a variable number of positional arguments to a function. So for instance, calculating future values or net present values is a good example, as projects have a variable number of cash flows. So in one project we have 4 years, and in the next project we have 10 years. However, our future value or net present value function should handle all cases. Let's assume we have the following investment with the following cash flows, and we have a required rate of return of 6%. And with the cash flows and the required rate of return, we can calculate the net present value of the investment project. So this is nothing new. And here we get 38. And now we can also define a function net present value. And we have actually 2 inputs or 2 parameters. So we need the required rate of return, and we need the cash flows or the values. And here we structure the NPV function in a way that we have to pass a sequence to the values parameter. So for instance, a tuple or a list. And then we iterate over the list. And for each and every element in the list, we calculate the present value, and then we add the present values. And finally, the function returns the net present value. So let's define the function here. And let's pass our required rate of return of 6% to the rate parameter, and the list CF to the values parameter. And no surprise, we also get here the 38.71. And now let's try to do the following. So we pass 7 positional arguments to the NPV function. So the required rate of return and each and every cash flow. And here we get an error message, and it says NPV takes 2 positional arguments, but 7 were given. So here we have to pass exactly 2 positional arguments. So one for the required rate of return, and then for the values parameter, actually a list with the cash flows. So this works. However, we can modify the NPV function in a way that also this works here. And we can actually define in the function header that we have the parameters rate and the star args. And this allows us to pass a variable number of positional arguments, And the very first argument is actually assigned to the rate parameter. And actually then star args exhausts all other positional arguments and creates a list. So let's define the function here. And then let's call the NPV function by passing 7 positional arguments. And by doing so, we assign R to the rate parameter and all other positional arguments to args. And also here we get the NPV of 38. And again, let me show you what actually happens in the background. So we have the 2 function parameters rate and star args, and we pass actually a tuple with 7 positional arguments. And then we have here the rate, which is 6%, and args is actually a list with all other elements. And finally, let me show you one last thing that actually does not work. So let's assume that we change here the sequence of star args and rate. So here in the beginning we have star args and rate. So let's define the function here. And then we can actually call the function by passing a variable number of positional arguments, so the cash flows here. And then we add the rate as a keyword argument. So this works. However, the following does not work. So if we simply pass 7 positional arguments, including R, then we get here an error message and it says NPV missing 1 required keyword only argument. So if we have star args followed by another parameters, then the following parameters or arguments are actually mandatory keyword arguments, so keyword only arguments. And actually this behavior is a bit surprising because the following works perfectly. So again, we have a tuple with these 7 elements, and here we can code the star args, rate, and this works here. And by doing so, we actually assign R to a rate, and star args exhausts all of the remaining elements. Alright, thanks for watching and see you in the next video. Bye. Alright, in this lecture I'm going to show you that a user-defined function can also return 2 or many results, and we have already seen this when we performed a t-test. So the t-test method returned the t-statistic and the p-value in a tuple. So now let's create a function that returns the net present value and the internal rate of return for an investment project. And we have the following investment project with the following cash flows. And we have a required rate of return of 6%. And then we can define the function NPV IRR. And we need 3 parameters. So we need the required rate of return, then the cash flows, and also we can pass a guess for the internal rate of return. And the default argument is 5%. So let's have a look at the function body. And first of all, we calculate here the net present value based on the cash flows and based on the required rate of return. And then here we calculate the internal rate of return with a while loop. So this is actually nothing new. And here we actually use the cash flows and also the guess. And then finally, let's have a look at the return statement. So we calculated the net present value and the IRR. And finally, we can say that we want to return the net present value and the final guess separated by a comma. So let's define the function here. And let's call the function NPV IRR by passing R to the rate parameter. So R is 6%. Then we pass our cash flow list CF to the values parameter. And we set the initial guess to 6%, for instance. And here we can see in the output a tuple with 2 values. So we have on the left-hand side the NPV, 38.71. And we have the final guess, which is very, very close to the IRR. So we have 11.91%. And last but not least, we can also unpack the results tuple. And then we call the function here. And by doing so, we saved the NPV in the variable NPV and the IRR in the variable IRR. And actually, we are not limited to 2 results, so this is completely variable and flexible. Alright, thanks for watching, and see you also in the next video. Bye. We are coming now to a very important concept in Python, scopes. So this is a quite complex topic we could spend a couple of hours on, and in this video I will give you a very practical and high-level overview on what you should really know about scopes. And the key message is, what happens in a function stays in the function, and what happens outside the function stays outside the function. So in a way, functions are pretty similar to Las Vegas. So functions and Las Vegas have their own scope, the local scope, which is separated from the rest of the code or the rest of the world, which is the so-called global scope. So let's have a look at a simple example, and let's assume that somewhere in our code we have saved 40 in the variable NPV. And then we have an investment project with the following cash flows, and we have a required rate of return of 6%. And then we can actually define the user-defined function NPV, where we can pass the rate, so the required rate of return and the cash flows, so this is nothing new. And then we can call the function by passing our required rate of return and the cash flow list. And this gives an NPV of 38.71. So we also printed here the intermediate results. And actually, as you can see here, we have in the function the variable NPV, and we have outside the function the variable NPV. And first of all, we set the value 40 to NPV, and then inside the function, we also have the variable NPV. And first of all, we set it to 0, and then we iterated over the cash flow list, and then we actually updated NPV several times. So from 0 to -200 to -181. And the final value for NPV here in the function is 38. And one could expect now that NPV is actually now 38. But NPV is still 40 as we defined here above. And the simple reason for this is that we have different and separated scopes. So here we have the variable in the global scope, which is referencing or pointing to 40. And then within the function here, we have the local variable or the function variable NPV. And this is completely separated from the global variable NPV. And even if we changed the local variable NPV several times, the global variable NPV is still 40, because here this is only a local variable or function variable that is separated from the global scope. So this is the local scope, the function scope, and this is the global scope. So here we are inside the function in the local scope, and NPV is a local variable, and therefore we cannot change here the global variable unless it is our intention. And there's a way also to change the global scope variable NPV. And we can actually do this with the keyword global. And here we can define that we also want to change the global variable NPV. So let's again run the cell here. And let's call the function. So here we get the same results, but now let's check the global variable NPV. So before we had 40, and now we have 38. So this is actually due to the global keyword. And there's even no need to define the global variable in advance. So we have here in the global scope no variable future value. We can check this. So the name future value is not defined, but we can actually define and create the global variable future value inside and within a function. So first of all, let's create the future value function, where we have to pass the present value, the interest rate, and the number of periods. And this is here the calculation. And finally, we return the future value. So let's call the function, and we get a future value of 121. So inside the future value function here, we created the local variable future value. But if we try to print future value in the global scope, then again we get here an error message. So in the global scope, future value is not defined. However, we can change this with the global keyword. So here we can define that the variable future value should also be in the global scope, and let's redefine the future value function, and let's call the function. And now we have also the global scope variable future value. All right, let's have another example, and let's have a equals 10 and b equals 20. And then we define the function my function, where we have to pass a and b. So here a and b are actually global variables, but here inside the function my function, a and b are actually local variables, so function variables. And the function myfunc actually increments the local variables a and b by 5, and then it returns a and b. And then we can actually pass the global a to local a and the global b to local b. So this is of course possible, and still those are separated. So let's run the cell here, and here we get 15 and 25. So actually the local variables a and b are 15 and 25, but the global variables a and b are still 10 and 20. Last but not least, let's come to a very important concept. So let's create the global variable a, and a is 10. And let's define now the function addition with one parameter, so the b parameter. And actually what the function does, it actually adds a and b, and here inside the function we create the local variable a, which is 100, and then we add a and b, and save the result in the function variable add, and finally we return add. So let's define the function, and let's call the function by passing 20. So we have b equals 20, and then we calculate here 100 plus 20, and we should actually return 120. And this is true. However, now let's cross out here a equals 100. So we do not define inside the function or the local variable a. And therefore, so let's define the function here. And therefore, if we call the function now, then first of all, Python looks in the local scope whether there is the variable a, and actually there is no variable a. And then Python goes to the next higher scope. In this example, it's the global scope. And here Python finds actually the global variable a and uses the value or the object that is stored in the global variable a. And if we pass 20 to the addition function, now we would expect the result actually 10 plus 20 gives 30. And this is true. So the key message is that Python first of all checks the local scope here and tries to find the variable a. And if Python cannot find the variable a, then it goes to the next higher scope, in this example here, the global scope. Alright, thanks for watching, and I'll see you also in the next video. Bye.